There's something pushing the Milky Way. Something invisible. Something powerful. And something we don't fully understand. For decades, astronomers have tried to map out what influences the movement of our galaxy. We know that the Milky Way, along with our entire local group of galaxies, is speeding through space at an astonishing rate, over 600 kilometers per second. But the real question is, why? What is causing this motion? For a long time, scientists believed we were being pulled towards something massive. A gravitational force in the universe, something dense and enormous, seemed to be dragging us in. They called it the Great Attractor. But then, something strange happened. When they mapped the universe in greater detail, they realized the picture was more complicated than they ever imagined. Yes, there was something pulling us in, but there was also something pushing us away. This mysterious force is what we now call the Dipole Repeller. It's not a physical object. It's not a galaxy, a star, or a black hole. It's a vast region of empty space, a cosmic void so devoid of matter that it actually repels galaxies away from it. And it's influencing the Milky Way's motion in a way we never expected. But how is that even possible? How can empty space push something as massive as an entire galaxy? To answer that, we have to go deep into the nature of the universe itself. Because the truth is, space isn't just empty nothingness. It's shaped by the distribution of matter, and the way galaxies move isn't just about what pulls them, it's also about what pushes them. The Dipole Repeller, this great emptiness, is one of the most mysterious and mind-bending concepts in astrophysics today. And the deeper we look into it, the more questions it raises. Is this just a normal part of the cosmic web, or is there something even more bizarre happening here? Could this be evidence of unknown physics? Something beyond our current understanding of gravity and dark energy? Or, an even crazier thought, could it be artificial? Could an advanced civilization be manipulating the universe itself? Let's dive into everything we know, and everything we don't, about this strange, invisible force that's shaping the motion of our galaxy. The idea that our galaxy is moving at incredible speeds through space isn't new. In fact, it's been known for decades. But figuring out exactly why has been one of the biggest challenges in cosmology. Initially, scientists believed we were being pulled towards something big, something heavy, something exerting a massive gravitational influence. This was the idea behind the Great Attractor. The Great Attractor is a dense region of galaxies located about 150 to 250 million light-years away in the direction of the Centaurus constellation. It has a gravitational pull so strong that it affects not just the Milky Way, but entire clusters of galaxies. And for a while, it seemed like the answer. It made sense, a massive collection of galaxies pulling everything toward it. But there was a problem. When scientists started mapping the cosmic microwave background, the afterglow of the Big Bang, they noticed something odd. The movement of the Milky Way wasn't just explained by the pull of the Great Attractor. There was an extra force involved, one that wasn't pulling us in, but pushing us away. This was the first clue that something else was at play. Something repelling us. The Dipole Repeller was first proposed in 2017, when astronomers used data from the Cosmic Flows 3 survey to map the movement of galaxies in unprecedented detail. What they found was stunning. Our galaxy wasn't just moving towards something, it was also being pushed away from an enormous void in space. Voids are some of the most bizarre structures in the universe. They're not just empty spaces between galaxies, they are regions where matter is incredibly scarce. Unlike the dense regions that make up galaxy clusters, voids contain very little, no stars, no galaxies, almost no matter at all. And yet, these voids can influence the movement of entire galaxies. Here's how it works. In a universe filled with galaxies, clusters, and voids, everything is affected by gravity. Areas with high density, like galaxy clusters, have strong gravitational pull. But voids, due to their lack of mass, don't exert that pull. Instead, they create a kind of gravitational imbalance. Imagine you're standing between two massive crowds of people. If one side is packed with thousands of people and the other side is completely empty, you'll naturally be pushed toward the emptier side as people move toward the dense crowd. In the same way, galaxies near a void get pushed away from it, simply because there's more mass pulling them in other directions. This is what's happening with the dipole repeller. It's a vast, almost incomprehensible empty region in space, and it's actually pushing our galaxy, along with many others, away from it. But here's where it gets even stranger. The dipole repeller isn't the only void in the universe. There are many, scattered throughout the cosmic web. But this one is special. It's unusually powerful. Its influence on the Milky Way's motion is so significant that it suggests something deeper about the way our universe is structured. Some scientists believe this might be evidence of something beyond our current understanding of gravity. Others think it could be linked to dark energy, the mysterious force that's accelerating the expansion of the universe. And then there's an even more mind-bending idea. What if this void isn't natural at all? Could an advanced civilization manipulate space on such a massive scale? The idea may sound like science fiction, but some physicists have speculated about the possibility of Kardashev Type 3 civilizations. Civilizations so advanced that they can alter the very structure of the universe itself. If such a civilization existed, one way they could manipulate the universe would be by creating vast voids, essentially, terraforming space on a cosmic scale. If this sounds impossible, remember that our own civilization is already experimenting with ways to manipulate gravity and energy on small scales. What if an ancient, hyper-advanced civilization had billions of years to develop such technology? Of course, this is just speculation. There's no direct evidence that the dipole repeller is artificial. But the fact that such a massive, empty void can exert such a huge influence on our galaxy raises fascinating questions about the nature of the universe itself. Could there be other repellers out there, shaping the motion of galaxies in ways we haven't yet discovered? Could our entire understanding of gravity and cosmic structure be missing something fundamental? The more we study the dipole repeller, the more it forces us to rethink what we know about the large-scale structure of the universe. It's not just about what's there, it's also about what's not there. And sometimes, the biggest mysteries come from the emptiest places. The concept of the dipole repeller forces us to rethink one of the most fundamental aspects of astrophysics: how gravity shapes the universe. Traditionally, we think of gravity as a purely attractive force. Massive objects pull in smaller objects, and large-scale structures in the universe are built around these gravitational wells. But the dipole repeller shows us that the absence of matter can be just as influential as its presence. To understand why, imagine the cosmic web, the vast structure of the universe that consists of galaxies, clusters, and enormous empty voids. These voids aren't just small gaps between galaxies. They can stretch for hundreds of millions of light years, containing almost no matter at all. The Milky Way is moving away from one such void at incredible speeds, and that's because gravity acts like a balance. On one side, you have the gravitational pull of dense galaxy clusters, like the Great Attractor. On the other side, you have the dipole repeller, where there's almost no gravitational influence pulling us back. This balance, or rather imbalance, is what propels the Milky Way. Think of it like a boat on a lake. If one side of the boat is being pulled by a strong current, while the other side is calm and still, the boat will naturally move toward the current. In our case, the calm side is the dipole repeller, an enormous nothingness, a region so empty that its lack of gravitational pull actually allows the Milky Way to be pushed away. What's even more intriguing is that this isn't just happening to our galaxy. Other galaxies in our region of space are experiencing the same effect. They are also being pushed away from the dipole repeller and pulled toward denser regions of the universe. This means that the dipole repeller isn't just a local anomaly, it's part of a much larger cosmic dance, shaping the motion of entire clusters of galaxies. But here's where things get even weirder. The dipole repeller may not be a single void, but rather a part of a network of voids that influence the entire structure of the universe. Some astronomers believe that voids like this are actually more common than we realize and that they play a key role in shaping how galaxies move on the largest scales. In fact, some theories suggest that voids could be connected in a way we don't yet fully understand. If voids interact with each other in a specific pattern, they could create a kind of anti-gravity effect, not because they're exerting a force, but because they allow galaxies to be influenced more strongly by the surrounding matter. And this brings up a huge question. Are voids like the dipole repeller simply the result of natural cosmic evolution, or is there something else at play? Because if the universe is shaped by a delicate balance of gravitational forces, then something as massive as the dipole repeller could hint at an underlying structure we haven't yet discovered. One possibility is that voids like this are a consequence of dark energy. Dark energy is the mysterious force that's causing the expansion of the universe to accelerate. We don't fully understand it, but we know it exists because the universe isn't just expanding, it's expanding faster and faster over time. Some scientists think that voids like the dipole repeller could be linked to dark energy in a way we haven't yet figured out. Perhaps these voids are regions where dark energy is more dominant, pushing galaxies away faster than normal space. If that's the case, studying the dipole repeller could give us a deeper understanding of what dark energy really is and how it shapes the universe. But there's another, even more mind-bending possibility. What if voids like the dipole repeller aren't just passive regions of empty space, but are actually evidence of something more profound, something that challenges our entire understanding of the universe? Some theories suggest that cosmic voids could be connected to the concept of the multiverse. The idea is that our universe might not be the only one. Instead, we could be part of a vast, infinite multiverse, with different universes coexisting alongside our own. If that's true, then voids like the dipole repeller could be boundaries, places where our universe interacts with another. This is, of course, highly speculative. But it raises an interesting question. What if voids aren't just empty space, but rather, points of transition between different parts of the cosmos? Could the dipole repeller be evidence that our universe is influenced by something outside of itself? And if that's true, what does it mean for our understanding of reality? Could we eventually find a way to study these voids in more detail and uncover evidence of a larger cosmic structure that we're only just beginning to perceive? These are the kinds of questions that keep astrophysicists awake at night. The dipole repeller is one of the strangest, most intriguing mysteries in modern cosmology. It challenges our understanding of gravity, dark energy, and the very structure of the universe itself. But perhaps the biggest question of all is this: if voids like the dipole repeller can influence galaxies on such a massive scale, could they be part of an even bigger, hidden force shaping the cosmos? Could there be a pattern to these voids, an unseen structure that determines the fate of entire galaxies and clusters? And if that's the case, what else is out there, hidden in the voids of space? If the dipole repeller is truly part of a larger pattern in the universe, then it forces us to consider something even more fundamental. Is there an unseen architecture to the cosmos, a hidden framework that determines how galaxies and clusters move across billions of light years? If such a structure exists, then we are not simply looking at random gravitational interactions. We are glimpsing a deeper design, one that has been shaping the universe for billions of years. This idea isn't just speculation. In recent years, astronomers have been uncovering evidence that the universe might be structured in ways we never expected. The discovery of massive cosmic filaments, vast tendrils of galaxies stretching across intergalactic space, has already shown that the universe is not a uniform, featureless void. Instead, galaxies are arranged in a web-like structure, forming an intricate cosmic network. But what if this structure is not just shaped by the presence of matter, but also by the absence of it? The dipole repeller suggests that voids may play just as important a role as galaxy clusters in shaping the overall movement of the universe. This would mean that our understanding of cosmic evolution has been missing a crucial piece. For decades, we have focused on how galaxies and clusters attract each other through gravity, forming massive superclusters. But if the dipole repeller and other voids exert an influence through their emptiness, then the universe's structure may be more dynamic than we ever imagined. Instead of a static web of matter, we might be living in a constantly shifting, ever-changing cosmic ocean, where galaxies flow through currents of gravitational push and pull. And this brings up an even deeper mystery. Why do voids like the dipole repeller exist in the first place? Are they simply the natural result of how matter was distributed in the early universe, or is there something more going on? One possibility is that voids were created during the earliest moments of the universe, during a period known as cosmic inflation. Inflation was a rapid expansion that took place just fractions of a second after the Big Bang. It stretched out space at an unimaginable rate, creating the seeds of the cosmic structures we see today. If inflation was not perfectly uniform, then some regions of space may have ended up with slightly more matter, while others ended up with almost none. Over billions of years, these tiny differences would have been amplified, creating the massive cosmic voids we see today. But there's another theory that's even more bizarre. Some physicists suggest that voids like the Dipole Repeller could be linked to something called quantum fluctuations, random energy variations that occurred during the early universe. If these fluctuations were large enough, they could have created regions of space where matter was permanently pushed away, forming voids that continue to influence the cosmos today. This idea ties into something even more profound: the possibility that the universe itself is shaped by quantum mechanics on a cosmic scale. If the Dipole Repeller is a remnant of quantum effects from the Big Bang, then we are looking at direct evidence that the largest structures in the universe are still being influenced by the weird, unpredictable nature of quantum physics. And this leads us to yet another possibility, one that might change how we think about the universe entirely. What if voids like the Dipole Repeller are not just empty space, but rather regions where different physical laws apply? This might sound like science fiction, but it's an idea that some physicists take seriously. According to certain theories, the universe may contain pocket regions where the laws of physics are slightly different. If this is the case, then voids could be more than just empty regions. They could be places where the fabric of reality itself behaves differently from the rest of the universe. This could help explain why galaxies are being pushed away from the Dipole Repeller. If space behaves differently inside the void, it might create a repulsive effect that influences the motion of surrounding galaxies. In other words, the Dipole Repeller might not just be a gravitational absence. It could be an actual force, something that actively shapes the universe in ways we don't yet understand. And if that's true, then the implications are enormous. Could there be other voids with similar effects, each one exerting a mysterious influence on the cosmic web? Could these voids be part of an even larger structure, one that extends beyond what we can currently see? Some scientists have even speculated that voids like the Dipole Repeller could be linked to dark matter, another massive cosmic mystery. Dark matter is an invisible substance that makes up most of the matter in the universe, but we can't see it or detect it directly. We only know it exists because of the way it affects galaxies and galaxy clusters. If dark matter interacts with voids in an unusual way, it could create strange gravitational effects that push galaxies around. This could mean that the Dipole Repeller isn't just an empty space. It could be a window into the hidden physics of dark matter itself. But here's where things get even more mind-blowing. Some researchers have suggested that voids might not just be passive regions of empty space. They could actually be gateways to something else. There is a theoretical idea that suggests voids could be connected to other universes. If the multiverse theory is correct, then our universe might be just one of many, existing side by side in a vast cosmic landscape. Some versions of this theory propose that voids like the Dipole Repeller could be areas where the boundary between universes is weaker. This would mean that what we perceive as a gravitational push could actually be an effect of another universe exerting influence on ours. It's an idea that sounds straight out of science fiction, but it's one that some physicists are seriously considering. And if that's the case, then the Dipole Repeller isn't just a mystery, it's a clue. A clue that suggests the universe is far stranger than we ever imagined, and that we are only just beginning to understand the true nature of reality. So the next time you look up at the night sky, remember this: the universe isn't just a collection of stars and galaxies. It's a living, shifting, evolving structure shaped by forces we can't yet fully explain. And somewhere out there, in the vast emptiness of space, lies a mystery that could change everything we know about the cosmos. The Dipole Repeller is just one example of how little we truly understand about the universe's large-scale structure. If it has the power to influence the Milky Way's motion across billions of light years, then what else might be out there, subtly shaping the very fabric of reality? Could there be other voids, just as powerful, hidden beyond our current observational limits? And if so, are they connected in some way, part of a much larger cosmic mechanism that we have yet to comprehend? One of the most intriguing aspects of this discovery is that it challenges our assumptions about how galaxies move. For decades, astronomers believed that the Milky Way's motion was dictated primarily by gravitational attraction, specifically by the Great Attractor, a massive cluster of galaxies pulling us in its direction. But the realization that we are also being pushed by a vast, empty void suggests that our understanding of cosmic motion has been incomplete. This raises the question, are voids just as important as galaxy clusters in determining the structure of the universe? Traditionally, scientists have focused on the regions of space that contain the most matter, clusters of galaxies, superclusters, and the dense filaments that form the cosmic web. These structures are thought to be the result of gravitational attraction, pulling together galaxies over billions of years. But if voids like the Dipole Repeller exert an influence of their own, then the story is far more complex. Consider what this means for our understanding of cosmic evolution. If voids actively push galaxies away, then they are not merely empty regions of space. They are dynamic, evolving structures that play a crucial role in shaping the universe. And if that's the case, then we need to rethink how the universe has developed over time. This brings us to another deep question: how do voids form in the first place? Scientists believe that the distribution of matter in the universe was determined by tiny quantum fluctuations that occurred just after the Big Bang. These fluctuations created slight variations in the density of matter, which then grew over billions of years due to the effects of gravity. The denser regions eventually formed galaxies and clusters, while the less dense regions became voids. But here's the catch: if voids are simply the leftover regions of space where matter was absent, why do they appear to have such a strong effect on galaxy motion? Shouldn't they be passive, rather than actively repelling matter? This suggests that there might be something more going on. One possibility is that voids are not truly empty, but rather contain some form of exotic energy that interacts with matter in a way we don't yet understand. Some researchers have proposed that dark energy, the mysterious force responsible for the accelerated expansion of the universe, might play a role in shaping voids. If dark energy is more concentrated in these empty regions, it could create a repulsive effect, similar to what we observe with the Dipole Repeller. But there's another, even stranger possibility. Some physicists have suggested that voids might be linked to the concept of modified gravity. In other words, our current understanding of how gravity works might not be entirely correct. If gravity behaves differently in large-scale voids, it could create the illusion that galaxies are being pushed away. This idea ties into some alternative theories of cosmology, including the idea that the universe's large-scale structure is influenced by unknown physical laws. Some models suggest that voids might be regions where space itself behaves differently, perhaps due to interactions with extra dimensions or even connections to other universes. If this is the case, then the Dipole Repeller might not just be an empty void, it could be a gateway to something even more profound. Some versions of string theory, for example, propose that our universe exists as a three-dimensional brane floating in a higher dimensional space. If voids like the Dipole Repeller represent regions where our universe is interacting with these extra dimensions, then the forces at play could be far stranger than anything we currently understand. And this brings up another mind-bending question: could voids be connected to the mysterious concept of dark flow? Dark flow is a term used to describe the unexplained motion of galaxy clusters that appear to be moving in the same direction, as if being influenced by something beyond the observable universe. Some researchers have speculated that this motion could be caused by the gravitational pull of massive structures lying outside our cosmic horizon, perhaps even entire parallel universes. If that's the case, then the Dipole Repeller might not just be a void, but part of a much larger structure that extends beyond what we can currently see. It could be a sign that our universe is not alone, but rather part of a vast, interconnected multiverse, where different regions of space interact in ways we have yet to understand. This idea might sound speculative, but it's not without precedent. Some versions of the inflationary universe theory predict that multiple, pocket, universes could form, each with its own unique properties. If our universe is just one of many, then the large-scale structures we observe, such as the Dipole Repeller, might be influenced by interactions with these other universes. And if that's the case, then we have to ask, what else is out there? Could there be other voids, even larger and more powerful than the dipole repeller, shaping the motion of galaxies across the cosmos? Could some of these voids be linked to forces we don't yet understand, possibly even influencing the fundamental nature of reality itself? These questions take us to the very edge of modern cosmology. The discovery of the dipole repeller has opened up an entirely new way of thinking about the universe, one where empty space is just as important as matter, and where vast cosmic voids might hold the key to some of the biggest mysteries in physics. And the more we study these voids, the more questions arise. Are they static, or do they evolve over time? Could they eventually merge or change shape, altering the movement of galaxies on an even larger scale? And if voids are truly repelling matter, what does that mean for the future of the universe? Some scientists believe that as the universe continues to expand, voids will grow larger and more dominant. If this happens, then over billions of years, galaxies might become even more isolated from one another, trapped within vast, empty spaces with little interaction. Eventually, the cosmic web itself could unravel, leaving behind a universe where matter is scattered across an immense void. But others suggest that there might be even more dramatic consequences. If voids like the dipole repeller are linked to unknown physical forces, then their influence could change over time, potentially leading to unexpected effects on the structure of the cosmos. Could they accelerate the expansion of the universe even further? Could they trigger new physical phenomena that we have yet to discover? One thing is certain: the more we learn about the dipole repeller, the more we realize how much we still don't know. It is a reminder that the universe is full of surprises, and that even the emptiest regions of space can hold profound secrets. And so, as we continue to explore the cosmos, we must keep asking questions, pushing the boundaries of our understanding, and searching for answers to the greatest mysteries of existence. Because somewhere out there, beyond the edge of what we can see, the universe is waiting to reveal its deepest secrets. The dipole repeller is just one example of how the universe constantly defies our expectations. For years, scientists assumed that galaxies moved primarily due to gravitational attraction. The discovery that voids, seemingly empty and featureless regions of space, could exert an influence just as significant as dense galaxy clusters forces us to rethink everything we thought we knew about cosmic motion. If voids can shape the universe in this way, what else might they be capable of? Could they be influencing the rate of cosmic expansion? Could they hold the key to understanding dark energy, the mysterious force that is causing the universe to expand at an accelerating rate? And if dark energy is concentrated in these voids, does that mean there is a fundamental connection between the empty spaces in the universe and the ultimate fate of everything we know? This concept changes the way we think about space itself. Traditionally, we imagine space as a vast emptiness, with galaxies and stars sprinkled throughout. But the more we study the large-scale structure of the universe, the more we realize that space is not uniform. It is shaped by forces we are only beginning to understand. The dipole repeller is proof of this, demonstrating that voids are not just passive gaps between galaxies, but active participants in the cosmic ballet that has been playing out since the dawn of time. One of the most striking implications of this discovery is what it suggests about the fundamental nature of the universe. If voids can push galaxies away, then the very structure of reality may be governed by forces that extend beyond gravity alone. Could there be a new type of interaction at play here, one that we have yet to uncover? Some physicists believe that voids like the dipole repeller might be revealing something deeper about the fundamental laws of physics. One possibility is that voids are shaped not just by the distribution of ordinary matter, but by the behavior of dark matter and dark energy on cosmic scales. Dark matter, the invisible substance that makes up most of the universe's mass, does not interact with light, making it nearly impossible to detect directly. But if dark matter behaves differently in voids compared to galaxy clusters, it could create strange effects, like the apparent repulsion we see from the dipole repeller. And what if voids are actually gateways to something even stranger? Some theories suggest that voids could be regions where the fabric of space-time itself is different. In these areas, the fundamental constants of physics might vary slightly, creating effects that we interpret as repulsion. Could it be that voids are regions where the very laws of nature break down, revealing glimpses of a deeper reality beyond our current understanding? This brings us to an even more mind-bending possibility. What if voids like the Dipole Repeller are connected to other universes? Some versions of string theory propose that our universe is just one of many, floating in a higher dimensional space known as the multiverse. If this is true, then voids might be places where the gravitational influence of neighboring universes leaks into our own. Could the Dipole Repeller be pushing us away because another universe is exerting a force on our own from the other side? While this might sound like pure speculation, some evidence suggests that something strange is happening on the largest scales of the cosmos. Observations of the cosmic microwave background, the faint radiation left over from the Big Bang, have revealed anomalies that some scientists believe could be caused by interactions with other universes. If this is the case, then voids like the Dipole Repeller might not be just empty regions of space, but windows into a far grander reality. Another possibility is that voids are not just empty regions, but instead filled with something exotic, perhaps a form of energy that repels matter. Some scientists have proposed that the nature of space-time itself might be different inside voids, leading to effects that mimic a repelling force. Could voids be reservoirs of unknown energy fields, influencing the movement of galaxies across billions of light years? If so, this could have profound implications for the ultimate fate of the universe. Right now, we know that the universe is expanding at an accelerating rate, driven by an unknown force called dark energy. But if voids contain concentrated pockets of this energy, then they might be playing a much bigger role in shaping the future of the cosmos than we previously realized. Could it be that voids are actively driving cosmic expansion? If the Dipole Repeller is pushing our galaxy away, could there be other voids, even larger and more powerful, contributing to the acceleration of the universe? And if so, does this mean that voids will eventually dominate the cosmos, stretching space apart until galaxies become completely isolated from one another? This leads us to one of the most unsettling possibilities of all, that the universe could end not in a fiery collapse, but in an eternal, cold emptiness. If the influence of voids continues to grow, then over billions of years, matter could become so spread out that no new stars form, no galaxies interact, and the universe becomes a dark, frozen wasteland. But there is another, even stranger idea. Some physicists believe that voids might not just passively shape the universe, they might be capable of evolving. If voids are regions where the fundamental nature of space itself is different, then they could change over time, leading to effects we can't even begin to predict. Could voids collapse? Could they merge? Could they create entirely new forms of matter or energy? And if voids are connected to the nature of space-time itself, then could they be responsible for some of the biggest mysteries in physics? Some researchers have speculated that voids could be linked to the origin of the universe itself. If the Big Bang was not the beginning, but rather the result of some deeper process, then voids might be the remnants of whatever came before. Could they be echoes of past universes? Could they hold clues to what existed before time itself? As we continue to explore the Dipole Repeller and other cosmic voids, we may find answers to some of the deepest questions about our existence. Are voids simply empty spaces, or are they part of a much larger cosmic mechanism? Do they hold the key to dark energy and the fate of the universe? Could they be revealing hints of new physics, new dimensions, or even other universes? For now, the Dipole Repeller remains a mystery. But the more we study it, the more we realize that the universe is far stranger than we ever imagined. Every discovery leads to new questions, new possibilities, and new challenges to our understanding of reality. And as long as those questions remain unanswered, one thing is certain: the universe will continue to surprise us. The Dipole Repeller is just one part of a much larger cosmic puzzle. Its existence challenges our conventional understanding of how galaxies move and forces us to reconsider the nature of empty space itself. But if voids like this can exert such a powerful influence, what else might be lurking in the vast, unseen fabric of the cosmos? One of the biggest questions that arises from the discovery of the Dipole Repeller is whether it is unique. Are there other voids exerting similar effects on different parts of the universe? If the Milky Way is being pushed by a repelling force, could other galaxies be experiencing the same thing? Some scientists believe that voids might play a fundamental role in shaping the large-scale structure of the cosmos. If so, then our entire view of cosmic motion may need to be reworked. Astronomers have already identified several large voids in the universe, some of which are so vast that they defy explanation. The Bode's void, for example, is one of the largest known voids, stretching nearly 330 million light-years across. It contains only a handful of galaxies, making it one of the emptiest regions in the observable universe. Could it also be exerting a repelling force on nearby galaxies? If so, how many of these voids are out there, subtly shaping the movements of entire galactic superclusters? This leads to a fascinating possibility. What if the entire universe is shaped by an intricate balance of attracting and repelling forces? We often think of gravity as the dominant force in the cosmos, pulling galaxies together and shaping the grand structures of the universe. But the discovery of the dipole repeller suggests that repelling forces, perhaps driven by the nature of space-time itself, may be just as important. Could there be a hidden network of voids and galaxy clusters working together to guide the motion of everything we see? Some cosmologists speculate that this might be the case, proposing that the universe is structured like a vast cosmic web. In this model, galaxies and matter are concentrated in filaments that weave through space, while massive voids act as the empty spaces in between. If voids are actively pushing matter away, then they may play a crucial role in maintaining this delicate balance. This also raises another question: what role do dark matter and dark energy play in this process? Dark matter is an invisible substance that makes up most of the universe's mass, yet we still don't fully understand what it is or how it interacts with normal matter. Some researchers believe that dark matter may behave differently in voids than it does in galaxy clusters, potentially explaining the repelling force we observe. If this is true, then voids could be laboratories for studying the nature of dark matter, providing crucial insights into one of the biggest mysteries in physics. Dark energy, on the other hand, is even more mysterious. It is the force that drives the accelerating expansion of the universe, but no one knows what it actually is. Some scientists have proposed that dark energy might be concentrated in cosmic voids, pushing galaxies apart and driving the overall expansion of space. If this is the case, then the dipole repeller might be a localized effect of a much larger phenomenon, one that could determine the ultimate fate of the universe. One of the most intriguing ideas is that voids like the dipole repeller might not be empty at all. Instead, they could be filled with exotic forms of energy, or matter that we have yet to detect. Some physicists speculate that voids could contain remnants of previous cosmic events, perhaps echoes of ancient fluctuations in the early universe that continue to shape the cosmos today. If so, studying these voids could reveal secrets about the origins of the universe itself. Another possibility is that voids could be connected to higher dimensional space. Some theories in physics, including string theory, suggest that our universe may be just one of many, existing within a larger, multidimensional reality. If this is true, then voids might be regions where the influence of other dimensions leaks into our own, creating strange effects like the repelling force observed in the dipole repeller. Could voids be weak points in the fabric of space-time, where the laws of physics behave differently than they do elsewhere? This idea might sound extreme, but some observations hint that the universe is not as uniform as we once thought. Anomalies in the cosmic microwave background, the faint radiation left over from the Big Bang, suggest that some regions of space may be influenced by unknown forces. Could these anomalies be evidence of interactions with other universes? If so, then voids like the dipole repeller might be the closest thing we have to a window into a higher reality. The implications of this are staggering. If voids are more than just empty spaces, then our entire understanding of the universe could be incomplete. What if voids are regions where new physical laws emerge? Could they be the birthplace of unknown forms of matter or energy? And if voids can push galaxies away, could they also pull them in under certain conditions? Some scientists have even speculated that voids could be sites of cosmic rebirth. In this scenario, voids might eventually collapse, triggering events similar to the Big Bang and creating new regions of space-time. If this is true, then voids like the dipole repeller might not just be passive features of the universe. They might be active participants in its ongoing evolution. But there's another possibility, one that is even more unsettling. If voids continue to expand and push matter away, then they could eventually dominate the universe, leading to a future where galaxies are so far apart that they can no longer interact. In this scenario, star formation would cease, and the universe would gradually fade into darkness. Could voids be the key to understanding how the cosmos will end? As we continue to study the dipole repeller and other cosmic voids, we are confronted with more questions than answers. Why do voids exist in the first place? What determines their shape and size? Are they truly empty, or do they contain hidden forces that we have yet to discover? And perhaps most intriguingly, could voids be revealing fundamental truths about the nature of reality itself? The more we learn, the more we realize how little we truly understand. The dipole repeller is just one mystery among many, but it serves as a reminder that the universe is far more complex than we ever imagined. Every discovery challenges our assumptions, forces us to rethink our theories, and opens new doors to the unknown. And perhaps that is the most exciting part of all. Because as long as there are mysteries like the dipole repeller, there will always be new questions to ask, new theories to explore, and new frontiers to uncover. The universe is a puzzle that may never be fully solved, but that's exactly what makes it so fascinating. The discovery of the dipole repeller has opened up an entirely new way of thinking about the forces that shape the universe. Traditionally, cosmologists have focused on the effects of gravity, how massive objects pull on each other, how galaxies form, and how the cosmic web is structured. But now, a counterintuitive idea has emerged, that vast voids, seemingly empty and devoid of matter, can also exert a force of their own. If this is true, it means that the movement of galaxies isn't just a result of attraction but also of repulsion. This challenges some of the most fundamental ideas in physics. Gravity, as we understand it, only pulls. It doesn't push. But the motion of the Milky Way suggests that something is pushing it, something that behaves as if it has a repelling force. Could this be an entirely new phenomenon? Or is it simply a consequence of the way mass is distributed in the universe? To understand this, scientists have turned to the idea of underdensities. In simple terms, an underdensity is the opposite of a galaxy cluster. Where a cluster has a high concentration of matter, a void has almost none. If you imagine space as a rubber sheet with heavy objects placed on it, gravity causes depressions, like valleys. Galaxies fall into these valleys because of gravitational attraction. But what happens in the regions where there are no objects? The sheet isn't being pulled downward in those areas, meaning that relatively speaking, the surrounding matter is being pushed away. This is what scientists believe is happening with the dipole repeller. The enormous void is creating an effect where galaxies seem to be repelled, not because of an actual force pushing them, but because there's nothing pulling them back. The result is an apparent movement away from the void, as if the Milky Way is being pushed out of a vast, empty region of space. But here's where things get even stranger. If the dipole repeller is just an absence of mass, why does it seem to have such a strong effect? Shouldn't its influence be weaker than that of massive clusters like the Shapley attractor? The fact that the dipole repeller has been identified as a major factor in our galaxy's motion suggests that voids might be far more important than we ever realized. This raises another fascinating possibility. What if the dipole repeller is connected to the mysterious force known as dark energy? Dark energy is the name given to the unknown force that is driving the expansion of the universe. It acts in opposition to gravity, causing galaxies to move away from each other at an accelerating rate. But no one knows what dark energy actually is. Could it be that voids like the dipole repeller are regions where dark energy is more concentrated? Some physicists have suggested that voids might play a critical role in the evolution of dark energy. In this scenario, voids aren't just empty spaces but reservoirs of an unknown force that pushes galaxies apart. If this is true, then studying voids could be the key to understanding the fate of the universe itself. But even if voids are just gravitational underdensities, their role in shaping the universe is undeniable. The cosmic web, the large-scale structure of the universe, is made up of filaments, clusters, and voids. These voids might be as important in determining galaxy motion as the massive structures themselves. If galaxies are being pulled toward massive clusters and simultaneously pushed away from voids, then our entire understanding of cosmic motion needs to be revised. One of the most intriguing aspects of the dipole repeller is how it was discovered. Unlike a galaxy cluster, which is easy to detect because of its bright galaxies, a void is almost invisible. It doesn't emit light. It doesn't have a clear structure. So how did scientists find it? The answer lies in velocity mapping. Instead of looking at objects themselves, scientists examined the motion of galaxies in three-dimensional space. They found that galaxies were not just moving toward known attractors like the Shapley supercluster, but were also moving away from an unseen region. By carefully mapping this motion, they identified a huge void, one that was effectively repelling our galaxy. This method of analysis represents a major shift in how we study the universe. Instead of just looking at where matter is, we now have to consider where it isn't. And if voids can have such a profound effect on the structure of the cosmos, what else might they be hiding? One possibility is that voids could be regions where the laws of physics behave differently. Some cosmologists have speculated that voids might be places where exotic forms of matter exist, perhaps remnants of ancient processes that shaped the early universe. If voids are filled with an unknown form of energy, they could be influencing cosmic motion in ways we don't yet understand. Another mind-bending idea is that voids might be linked to the concept of multiverses. Some theories suggest that our universe is just one of many, and that other universes exist in parallel with our own. Could voids be places where the influence of other universes leaks into ours? If so, the dipole repeller might not just be an ordinary void, it might be something much stranger. There's also the question of how voids evolve over time. Are they growing larger? If so, what happens when a void becomes so large that it dominates a region of space? Some scientists believe that voids are slowly expanding, pushing galaxies further apart. If this trend continues, then voids might eventually become the most dominant feature of the universe. In a far future scenario, matter could become so scattered that galaxies stop forming altogether. The universe would become a vast, empty expanse, a cosmic desert dominated by nothingness. But we're not there yet. Right now, we're still trying to understand the dipole repeller and what it means for our place in the cosmos. The more we study it, the more questions arise. Why is this void so powerful? Are there other voids exerting similar influences? And could this discovery lead us to entirely new physics? The story of the dipole repeller is a reminder of how much we still have to learn about the universe. It challenges our assumptions, forces us to reconsider what we think we know, and opens up new avenues of exploration. It is a mystery that will likely take years, if not decades, to fully unravel. But that's the beauty of science. The deeper we look, the more mysteries we find. And perhaps that's the real lesson of the dipole repeller. The universe is not just a collection of objects and forces that we can neatly explain. It is a dynamic, evolving mystery, full of surprises waiting to be discovered. And as long as we keep looking, we will continue to uncover new and astonishing truths about the cosmos. The dipole repeller is more than just an empty space in the universe. It's a puzzle that forces us to rethink how cosmic forces interact. Traditionally, we assume that gravity is the primary driver of galaxy motion. Massive clusters pull galaxies in, shaping the cosmic web. But here we have a void, an absence of matter, seemingly exerting influence over our entire galactic neighborhood. The concept of repulsion on such a large scale is difficult to wrap our heads around. If the dipole repeller is truly affecting the motion of galaxies, then voids may be just as significant as galaxy clusters in determining the large-scale structure of the universe. This changes everything we thought we knew about cosmic evolution. If voids like the dipole repeller play an active role, then we need to start mapping them just as carefully as we map galaxy clusters. In fact, what if there are more dipole repeller-like voids scattered throughout the universe? Could other galaxies be moving due to similar effects, influenced not just by attraction but by repulsion from empty regions? If so, the entire model of cosmic motion needs to be rewritten. The idea of voids influencing galaxy motion might seem strange, but it actually fits within the broader context of how the universe behaves on large scales. The cosmic microwave background radiation, the faint afterglow of the Big Bang, shows tiny fluctuations in temperature that correspond to regions of slightly higher or lower density. Over billions of years, these tiny differences grew into the massive structures we see today, with dense regions forming galaxies and underdense regions becoming voids. But if these voids have an active role in shaping cosmic motion, then perhaps the process of structure formation is even more complex than we realized. One of the most intriguing implications of the dipole repeller is how it relates to dark energy. Dark energy is the mysterious force that is causing the universe to expand at an accelerating rate. While we don't know what dark energy is, we do know that it acts in opposition to gravity. Could voids like the dipole repeller be regions where dark energy is more concentrated? If so, this could help explain why they seem to push galaxies away. Some scientists have even proposed that voids might be the key to understanding the fate of the universe. If voids continue to grow and push galaxies apart, then over time, matter will become more and more isolated. In a distant future, galaxy clusters could be separated by enormous empty spaces, with no new galaxies forming. The universe would become a vast, empty void, dominated not by matter but by dark energy. This raises another fascinating question. If voids are growing, what happens to the matter that was once inside them? When we look at the dipole repeller, we see a region that is almost completely devoid of galaxies. But was it always like this? Could it be that, billions of years ago, this region had more matter that was slowly pushed outward? If so, then voids might not just be passive empty spaces. They could be actively expanding over time. This leads to an even wilder possibility. What if voids like the dipole repeller are connected to something even bigger? Some theories suggest that the universe might be structured like a vast network of expanding and contracting regions. If voids are growing and pushing matter outward, could it be that they are connected to other, larger voids? Could voids eventually merge, creating supervoids that shape entire regions of the cosmos? The concept of supervoids isn't just theoretical. In fact, astronomers have already discovered some of the largest voids ever observed, including the Boötes void, a massive empty region in space that contains almost no galaxies. If the dipole repeller is part of a larger network of voids, then its influence might extend far beyond what we currently understand. One of the biggest challenges in studying the dipole repeller is that it's almost invisible. Unlike a galaxy cluster, which can be easily detected because of its bright galaxies, a void doesn't emit any light. This makes it incredibly difficult to study. Scientists have had to rely on indirect methods, like analyzing galaxy motions, to infer its presence. But what if there are other voids out there that we haven't even detected yet? Could there be even larger voids shaping the structure of the universe in ways we haven't considered? Another major question is whether the dipole repeller is unique. Is it the only void exerting a repelling force on galaxies, or are there others? If there are multiple voids influencing galactic motion, then we may need to completely rethink how we model cosmic expansion. Instead of seeing the universe as a collection of gravitational attractors, we may need to consider a more dynamic system, where voids and clusters work together to shape the movement of galaxies. If this idea holds true, it could change the way we understand the formation of galaxies themselves. We usually think of galaxies forming in regions of high density, where matter clumps together due to gravitational attraction. But what if voids play an active role in this process as well? Could the movement of matter away from voids help seed the formation of new galaxies? If so, then voids might not just be empty spaces. They could be essential components of cosmic evolution. One of the most mind-blowing possibilities is that voids like the dipole repeller could be linked to exotic physics. Some researchers have suggested that voids might be places where the laws of physics behave differently. Could voids contain exotic forms of matter that we haven't discovered yet? Could they be windows into other dimensions or even alternate universes? While these ideas are purely speculative, the fact that voids seem to have such a strong influence on galaxy motion suggests that there is much more to learn. Another strange aspect of the dipole repeller is that its effect seems to be incredibly large-scale. The Milky Way is not a small galaxy, it's a massive structure containing hundreds of billions of stars. For a void to have such a strong effect on its motion, it must be enormous. This suggests that voids are not just local phenomena but may be fundamental components of the large-scale structure of the universe. If voids like the Dipole Repeller are truly shaping the cosmos, then they may also hold the key to understanding some of the biggest mysteries in physics. For example, the nature of dark matter and dark energy remains one of the greatest unsolved questions in science. Could voids be revealing something about these mysterious forces? If voids are regions where dark energy is more concentrated, then studying them could provide new insights into the fundamental forces driving the expansion of the universe. The Dipole Repeller is a reminder that the universe is far more complex than we ever imagined. Just when we think we have a solid understanding of how things work, new discoveries force us to rethink everything. The fact that an empty region of space can have such a profound effect on galactic motion challenges our most basic assumptions about how the universe operates. What makes this discovery even more exciting is that it opens up new possibilities for exploration. If voids are playing an active role in shaping the cosmos, then we need to start studying them in greater detail. Future telescopes and surveys could help map these voids more accurately, revealing their true extent and influence. The Dipole Repeller is not just a strange anomaly, it is a clue to a much deeper mystery. It suggests that the forces shaping the universe are more complex than we ever realized. And if we can understand how voids interact with galaxies, dark matter, and dark energy, we may be one step closer to answering some of the biggest questions in cosmology. But for now, the mystery remains. The Dipole Repeller is out there, silently influencing the motion of galaxies, shaping the universe in ways we are only beginning to understand. What else might it be hiding? The mystery of the Dipole Repeller is not just about an empty space pushing galaxies away. It's about the hidden forces shaping the very structure of the universe. When we think about space, we often picture a vast emptiness dotted with galaxies, but in reality, space is structured in a way that resembles an intricate web. This cosmic web consists of filaments of matter, where galaxies and clusters form, separated by enormous voids. The Dipole Repeller is one of these voids, but what makes it so strange is that it seems to have a measurable effect on our galaxy's motion. To truly grasp the significance of this, we have to reconsider how cosmic structures form in the first place. After the Big Bang, the universe was almost uniform, with only tiny fluctuations in density. Over billions of years, gravity pulled matter together into dense regions, forming galaxies and clusters, while the less dense regions became voids. But if voids are actively influencing galactic motion, then they may not be passive byproducts of structure formation. They may be dynamic players in shaping the cosmos. The Dipole Repeller is located opposite the Shapley supercluster, a massive concentration of galaxies that is pulling the Milky Way and other nearby galaxies toward it. At first glance, it might seem like the Shapley supercluster is solely responsible for our motion, but when astronomers mapped the distribution of galaxies and their velocities, they noticed something strange. There was a clear dipole pattern, meaning that galaxies weren't just moving toward Shapley, they were also moving away from a specific underdense region. That region is the Dipole Repeller. This discovery suggests that our motion through space is not just due to gravitational attraction but also to a kind of repulsion from voids. This doesn't mean that voids are exerting a physical pushing force. Rather, they create an imbalance in the gravitational landscape. Imagine rolling a ball on a bumpy surface. If there's a deep valley on one side and a hill on the other, the ball will move toward the valley, not because it's being pushed, but because the landscape itself is shaping its motion. The same thing is happening on a cosmic scale. Our galaxy is not just being pulled toward dense regions, but it's also moving away from voids like the Dipole Repeller. This raises a fundamental question. If voids can influence motion, how many other voids are playing a role in shaping the large-scale structure of the universe? The Dipole Repeller is just one void, but the universe is filled with these empty regions. Could they be responsible for other unexplained motions of galaxies? Are there even larger voids exerting an effect that we haven't detected yet? Another major question is whether the Dipole Repeller is growing over time. If voids expand while matter clumps together, then the repeller could be getting larger, which would mean its influence on galaxy motion could be increasing. This would have major implications for the future of the universe. If voids continue to grow and push galaxies apart, then over time, the cosmic web itself could become stretched thinner and thinner. Eventually, in the far future, galaxies could be so isolated that they no longer interact with one another, leaving a universe dominated by vast, empty spaces. But what exactly is happening inside the dipole repeller? Since it's an underdense region, we know there is very little matter, but does that mean it's completely empty? Not necessarily. There could still be diffuse gas, dark matter, or even exotic particles that we haven't yet discovered. Some researchers have suggested that voids might be places where dark energy is more concentrated. If that's true, then the dipole repeller could be providing a rare glimpse into how dark energy operates. Dark energy is one of the biggest mysteries in physics. We know it's causing the universe to expand at an accelerating rate, but we have no idea what it actually is. If voids like the dipole repeller are regions where dark energy has a stronger presence, then studying them could help us understand what dark energy is and how it affects the universe. Some scientists have even proposed that voids might be linked to the fundamental nature of spacetime itself. Could voids be regions where the geometry of space is different? Could they be connected to other parts of the universe in ways we don't yet understand? These are questions that push the boundaries of modern physics. But the fact that the dipole repeller has such a measurable effect on galaxies suggests that there is much more going on in these empty regions than we previously thought. The idea that voids could be shaping the cosmos also has implications for our understanding of cosmic expansion. Right now, we assume that galaxies are primarily influenced by the gravity of other galaxies. But if voids have an active role, then we need to rethink how we model large-scale motions. Are galaxies in other parts of the universe also being influenced by similar voids? Could our entire observable universe be shaped by a vast network of repelling forces that we have yet to fully understand? Another fascinating possibility is that voids might play a role in the evolution of galaxies themselves. We typically think of galaxies forming in dense regions where matter clumps together, but what if the movement of galaxies away from voids also contributes to their formation? If voids help funnel matter into certain regions, they could be indirectly responsible for the birth of new galaxies. This would mean that voids are not just passive empty spaces but are actively shaping the structure of the universe in ways we have only begun to uncover. One of the biggest challenges in studying the dipole repeller is that it doesn't emit any light, making it incredibly difficult to observe directly. Instead, scientists have to rely on indirect methods, such as mapping the velocities of galaxies and analyzing their distribution. But as our technology improves, we may be able to probe these voids more directly. Future telescopes, such as the Vera C. Rubin Observatory and the Euclid Space Mission, will provide deeper insights into the structure of the universe, potentially revealing more about how voids influence cosmic motion. The dipole repeller is a reminder that the universe is full of surprises. Just when we think we have a clear picture of how things work, new discoveries force us to rethink our understanding. The idea that an empty region of space can influence the motion of galaxies challenges our most fundamental assumptions about gravity and cosmic structure. If voids can play an active role in shaping the universe, then we have to reconsider everything from galaxy formation to the nature of dark energy. What's even more exciting is that the dipole repeller might not be the only one. If this void has such a strong effect on galaxy motion, then there could be others scattered throughout the universe. Some of them might be even larger, with effects that extend across billions of light years. If we can map these voids and understand how they interact with the rest of the universe, we could unlock new insights into the forces that govern cosmic evolution. For now, the dipole repeller remains one of the most intriguing mysteries in cosmology. It challenges our understanding of how galaxies move, raises new questions about the role of voids, and hints at deeper connections between gravity, dark energy, and the structure of spacetime itself. As we continue to explore the universe, discoveries like this remind us that space is far from empty. It is a dynamic, ever-changing landscape shaped by forces we are only beginning to understand. The implications of the dipole repeller extend beyond just our local cosmic neighborhood. If voids like this can influence the movement of entire galaxies, then our entire understanding of large-scale cosmic flows needs to be reconsidered. Scientists have long believed that galaxy movements were primarily dictated by gravitational attraction, but the presence of a repelling force, one that doesn't come from a dense mass, but rather from the absence of it, changes everything. It means that our models of the universe's structure need to account not just for the pull of superclusters but also for the push of vast voids. This could explain some of the strange motions of galaxies that we've observed throughout the universe. When astronomers map the cosmic microwave background radiation, the afterglow of the Big Bang, they see a dipole pattern in its temperature. This indicates that our entire galaxy is moving relative to this cosmic backdrop. And while some of this motion can be explained by the pull of dense regions like the Shapley supercluster, the presence of the dipole repeller suggests that we're also being pushed. The idea that both attraction and repulsion shape cosmic flows means that voids could be just as important in dictating galaxy movements as the massive structures we've traditionally focused on. But what causes this repelling effect? It's not like the dipole repeller is exerting a physical force in the way that a magnet repels another magnet. Instead, it comes down to how gravity works in the large-scale structure of the universe. In denser regions, gravity pulls matter inward, creating clusters and filaments where galaxies accumulate. In voids, however, there is much less mass, meaning there is less gravitational pull. As a result, galaxies on the edges of voids feel a stronger pull from the denser regions around them, causing them to drift away from the void itself. In this way, voids act as repellers not because they push matter away, but because they lack the gravity to hold onto it. This raises an even more intriguing question: could the dipole repeller be growing? If galaxies continue to move away from it, then the void itself could be expanding, making it an even larger influence on the surrounding cosmic structure. This would mean that voids aren't just passive spaces left over after galaxies form. They could be dynamic regions that evolve over time. Some theories suggest that voids may even be linked to the mysterious force known as dark energy, which is responsible for the accelerating expansion of the universe. Dark energy is one of the biggest mysteries in modern physics. We know that it exists because the universe's expansion is speeding up rather than slowing down, but we don't know what it actually is. Some researchers have proposed that voids could be regions where dark energy is more dominant. If that's the case, then studying the dipole repeller could provide crucial insights into what dark energy is and how it behaves. The idea that voids might be special regions in the universe isn't new. Some theories suggest that the large-scale structure of the universe is shaped not just by gravity but by the interplay between dark matter and dark energy. Dark matter, which makes up most of the universe's mass, is responsible for pulling galaxies together, while dark energy pushes them apart. If voids are regions where dark energy dominates, then they could be the key to understanding why the universe's expansion is accelerating. This could also explain why the dipole repeller has such a noticeable effect on our galaxy's motion. If dark energy is more concentrated in voids, then it could be playing a role in pushing galaxies away from these underdense regions. This would mean that the dipole repeller isn't just an empty space. It could be a window into the fundamental forces shaping the universe. But there's another possibility that's even more mind-bending. What if voids like the dipole repeller aren't just empty spaces, but regions where the fabric of space itself behaves differently? Some physicists have proposed that voids might be places where the geometry of spacetime is different from the regions where galaxies cluster. If that's true, then voids could be acting as natural laboratories for testing the limits of general relativity and other theories of gravity. This could have profound implications for our understanding of the universe's fate. If voids are expanding and influencing the motion of galaxies, then over time, they could reshape the entire cosmic web. In the distant future, galaxies could become even more isolated as they move further apart, eventually leaving a universe where vast empty voids dominate the landscape. If dark energy continues to accelerate the expansion of space, then these voids could become so large that galaxies lose contact with one another entirely, leading to a cosmos where every galaxy is alone in an ever-expanding void. Another fascinating aspect of the dipole repeller is that it challenges our assumptions about what counts as something in the universe. We tend to think of space as being defined by the things inside it, stars, galaxies, and clusters. But the dipole repeller shows us that even the empty regions of the universe can have a tangible effect on the things around them. It suggests that nothingness itself is not truly empty, but a critical component of the cosmic landscape. If this is true, then voids could be just as important in shaping the evolution of the universe as the massive galaxy clusters we've traditionally focused on. Instead of thinking about the universe as being defined by where the matter is, we might need to start thinking about it in terms of where the matter isn't. This shift in perspective could lead to a deeper understanding of cosmic evolution, revealing new insights into how galaxies form, move, and interact over billions of years. What's even more exciting is that the dipole repeller might not be unique. If this void has such a strong effect on galaxy motion, then there could be other voids throughout the universe that are playing similar roles. Some of these voids might be even larger, affecting galaxies across vast distances. If we can identify and map these voids, we might be able to uncover an entirely new layer of the cosmic web, one that is shaped not just by gravitational attraction, but by the hidden influence of repelling voids. The discovery of the dipole repeller is a reminder that the universe is far more complex than we ever imagined. Just when we think we understand the forces that shape our cosmos, new discoveries force us to rethink everything. The idea that voids can influence the motion of galaxies challenges our fundamental assumptions about gravity and cosmic structure. It raises new questions about the nature of dark energy, the evolution of the universe, and even the fundamental properties of spacetime itself. As technology advances, we will be able to probe the dipole repeller and other voids in greater detail. Future telescopes like the Euclid Space Mission and the Vera C. Rubin Observatory will provide deeper insights into the structure of the universe, helping us to unravel the mysteries of these cosmic voids. With every new discovery, we come closer to understanding the hidden forces that shape our universe. The dipole repeller is more than just a void, it's a glimpse into the unknown. It challenges everything we thought we knew about how galaxies move and forces us to consider new possibilities about the structure of the cosmos. As we continue to explore the universe, we may find that the greatest mysteries aren't in the galaxies themselves, but in the vast, empty spaces between them. The idea that voids like the dipole repeller could play a crucial role in the structure of the universe forces us to reconsider our entire perspective on cosmic evolution. For decades, astronomers focused almost exclusively on the large-scale structures that shape the cosmos, superclusters, galaxy filaments, and dense regions of matter. But the dipole repeller reminds us that the empty spaces between these structures are just as important. These voids aren't passive gaps in the cosmic web. They actively shape the motion of galaxies. To truly grasp the importance of this, let's think about it in another way. Imagine you're in a crowded room, and everyone around you starts walking toward one side. Naturally, you'll find yourself moving in that direction too, even if you aren't being pulled by anything specific. Now, imagine that the opposite side of the room is completely empty, with no people at all. Without anyone to slow you down, you'd move even faster toward the crowd. This is essentially what's happening with the dipole repeller. Our galaxy is moving away from this vast void not because it's being physically pushed, but because the gravitational pull of denser regions is stronger in the other direction. What makes this even more fascinating is that the dipole repeller isn't just affecting the Milky Way, it's influencing entire clusters of galaxies. The local group, which includes the Milky Way and Andromeda, is just one small part of a much larger movement. When astronomers map out the motion of galaxies in our region of space, they find a pattern that points toward a balance of forces. On one side, we're being pulled by dense regions like the Shapley supercluster, and on the other, we're moving away from a vast, empty void. This means that cosmic voids aren't just anomalies. They're fundamental components of the way the universe works. But here's where things get even weirder. The dipole repeller may not be a singular phenomenon. In fact, some scientists believe that multiple voids throughout the universe could be playing similar roles. If so, then the large-scale structure of the cosmos might be governed by an intricate balance between attraction and repulsion. Instead of just thinking about gravity as a force that pulls things together, we need to think about it as a dynamic system where the absence of matter can be just as influential as its presence. One of the most intriguing aspects of this discovery is that it could help solve a long-standing mystery in cosmology: the peculiar motion of our galaxy. For years, astronomers have known that the Milky Way isn't just orbiting within the local group. It's moving at incredible speeds relative to the cosmic microwave background, the faint afterglow of the Big Bang. This motion, often referred to as the peculiar velocity of our galaxy, didn't fully match up with the gravitational influences we had identified. The presence of the dipole repeller provides a missing piece of the puzzle. It suggests that our motion isn't just a result of being pulled by other galaxies. It's also shaped by the voids we're moving away from. This discovery opens up an entirely new area of research in cosmology. If voids can influence galaxy motion on such a large scale, then we need to start mapping them more carefully. Advanced surveys of the universe, such as those conducted by the Sloan Digital Sky Survey and future missions like the Nancy Grace Roman Space Telescope, will help us create detailed maps of these voids. By studying their distribution, we can better understand how they interact with galaxies and what role they play in the overall expansion of the universe. But there's another, even deeper question: could voids like the dipole repeller tell us something about the fate of the universe itself? Right now, we know that the universe is expanding at an accelerating rate due to the influence of dark energy. But what if voids are somehow connected to this process? Some theories suggest that the presence of large voids could enhance the effects of dark energy, making the expansion even faster. If that's true, then voids might not just be passive structures. They could be active components in the ultimate destiny of the cosmos. This also raises questions about the nature of dark energy itself. Could it be more concentrated in voids? Is there something about these empty regions that amplifies its effects? Right now, we don't know, but future studies of cosmic voids could provide new insights into the very fabric of the universe. Even more mind-bending is the idea that voids might not just be empty, but instead contain unknown forms of energy or matter that we haven't yet detected. Some alternative theories of physics suggest that voids could be places where exotic phenomena occur, perhaps even regions where our understanding of gravity breaks down. If that's the case, then studying voids like the dipole repeller might not just help us understand galaxy motion. It could help us unlock entirely new laws of physics. Ultimately, the discovery of the dipole repeller is a reminder that the universe is full of surprises. Just when we think we have a solid understanding of how cosmic forces work, something unexpected emerges and forces us to reconsider everything. The fact that an empty void, something that we once thought of as insignificant, could have such a profound effect on galaxy motion is a testament to the complexity of the cosmos. As we continue to explore the universe, we may find that the dipole repeller is just the beginning. Other voids, perhaps even larger and more influential, could be out there, shaping the motion of galaxies on a grand scale. With new telescopes and advanced simulations, we're on the verge of uncovering even more secrets about the nature of space itself. The more we study these vast, empty regions, the more we realize that they are not empty at all. They are an essential part of the cosmic dance that has been playing out for billions of years. The implications of the dipole repeller go beyond just understanding the motion of our galaxy. It challenges our fundamental assumptions about how the universe is structured. For centuries, we have understood gravity as a force that attracts, pulling objects toward one another. But this discovery forces us to consider the idea that empty space itself can play an equally significant role, acting as a sort of repelling force not because it physically pushes objects away, but because it lacks the gravitational influence that denser regions exert. This shift in perspective is crucial, as it may redefine how we interpret large-scale cosmic motion. To put it another way, the dipole repeller is like a hole in a fabric stretched tightly across a frame. If you press down on one part of the fabric, representing a dense region of galaxies, it creates a dip, and objects naturally fall toward it. But if there's a hole in the fabric, representing the void, then there's no support, and objects near the hole will move away from it simply because there's nothing to hold them back. This is essentially what's happening with the dipole repeller. It's not exerting a force in the traditional sense. Rather, it creates an imbalance in the gravitational field that causes galaxies to shift their motion accordingly. This realization forces us to rethink how cosmic structures form and interact. We often focus on galaxy clusters, dark matter filaments, and the cosmic web that connects them, but the vast empty spaces in between are just as important. The Dipole Repeller, along with other voids like it, may be shaping the universe in ways we never previously considered. One of the biggest questions now is, how many dipole repellers exist? Is this a unique phenomenon, or are there multiple voids throughout the universe playing similar roles? If the latter is true, then the large-scale structure of the universe may be shaped by a balance of attractions and repulsions, creating a cosmic equilibrium that has governed the movement of galaxies for billions of years. Astronomers are already working to identify other voids that might function similarly to the Dipole Repeller. Advanced surveys, such as the Dark Energy Survey and the upcoming Vera C. Rubin Observatory, will provide incredibly detailed maps of the universe, allowing researchers to detect more of these mysterious empty spaces. By analyzing how galaxies move in relation to them, we can determine whether voids have a consistent effect on cosmic dynamics or if the Dipole Repeller is an anomaly. Another fascinating implication of the Dipole Repeller is its potential connection to dark energy. We already know that the universe is expanding at an accelerating rate, driven by some unknown force. Dark energy is currently the best explanation for this phenomenon, but its nature remains a mystery. Some researchers speculate that voids like the Dipole Repeller could provide clues about how dark energy operates. For instance, if voids are more prominent, or have a stronger effect than we previously thought, they might amplify the expansion of the universe. The empty spaces in between galaxies could act as accelerators, enhancing the push of dark energy and driving cosmic expansion even faster. This would mean that voids aren't just passive gaps in the cosmic web, they could be active participants in the fate of the universe itself. One of the most exciting possibilities is that voids may contain unknown properties that affect cosmic motion. Could they harbor forms of energy we haven't yet detected? Could the laws of physics operate differently in these vast empty regions? These are questions that astronomers and physicists are eager to explore. As technology advances, we will be able to study voids in even greater detail. Future space telescopes, such as the James Webb Space Telescope's successors and potential missions dedicated to mapping cosmic voids, could provide direct measurements of how these regions influence galaxy motion. Computer simulations, powered by artificial intelligence and vast datasets, will allow scientists to recreate the effects of voids on a grand scale, offering insights into how they shape the universe. The Dipole Repeller is more than just a single discovery. It's the beginning of a new way of thinking about cosmic structure. It challenges the traditional view of gravity as the dominant force in the universe and suggests that the absence of matter is just as important as its presence. This could revolutionize our understanding of how galaxies move, how cosmic expansion works, and even the ultimate fate of the universe. What if voids like the Dipole Repeller are not just shaping galaxy motion but also influencing the very fabric of space-time? Could they be linked to unknown forces or hidden dimensions? The more we learn about these vast, empty regions, the more questions arise. Ultimately, the study of voids will become one of the most important areas of cosmology in the coming decades. As we refine our understanding of the universe, we may find that the Dipole Repeller is not an outlier but a fundamental component of cosmic evolution. This discovery could lead to breakthroughs that reshape everything we thought we knew about the universe. The journey to understanding the Dipole Repeller is just beginning. With every new observation, every refined simulation, and every deeper analysis of the cosmic web, we move one step closer to unraveling one of the greatest mysteries of space. And as we do, we may find that the universe is far stranger, more dynamic, and more interconnected than we ever imagined. The concept of the Dipole Repeller forces us to reconsider the way we perceive cosmic motion, not just on a local scale but across the entire observable universe. If vast empty regions can influence the motion of galaxies as significantly as dense galaxy clusters, then we are only scratching the surface of understanding the forces shaping the cosmos. One of the most intriguing aspects of this discovery is how it fits into the larger framework of cosmic voids. Voids are not just empty spaces. They are essential components of the large-scale structure of the universe. The cosmic web, a vast network of galaxies, filaments, and clusters, is defined not only by where matter is concentrated but also by where it is absent. These voids make up the majority of the universe, yet they remain one of the least studied aspects of cosmology. Traditionally, when astronomers study the universe, they focus on what they can see: stars, galaxies, clusters, and the filaments that connect them. But the dipole repeller suggests that the voids, the areas where matter is missing, are just as important, if not more so. The sheer scale of these voids is mind-boggling. Some are hundreds of millions of light-years across, vast expanses of nearly nothingness where only the occasional faint galaxy can be found. These voids are not simply empty. They are regions with lower-than-average matter density, meaning they exert far less gravitational pull compared to denser areas. The existence of these voids has been known for decades, but only recently have astronomers begun to appreciate their role in shaping cosmic motion. The dipole repeller is a prime example of this newfound perspective. Instead of being mere gaps between galaxies, voids may actively influence the movement of matter on the largest scales. If this is true, then voids could be fundamental to understanding the forces that govern the universe. One of the key questions scientists are now exploring is whether the dipole repeller is unique, or if similar voids exist elsewhere. If voids of similar scale and influence are found, it would mean that our galaxy is not experiencing a one-of-a-kind phenomenon but rather a common feature of cosmic evolution. This could reshape our understanding of how galaxies move and interact over billions of years. New telescopes and advanced simulations will help scientists analyze these voids in greater detail. Future observational projects, such as the Euclid mission and the Square Kilometre Array, will provide unprecedented maps of cosmic structure, potentially identifying other voids with similar repelling effects. By studying how galaxies move in relation to these voids, researchers can determine whether voids consistently act as cosmic repellers or if the dipole repeller is an unusual case. The implications of the dipole repeller also extend to our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy remains one of the biggest mysteries in physics, and while it is generally thought to be a uniform property of space itself, some scientists believe that cosmic voids might hold crucial clues to its nature. One theory suggests that voids could amplify the effects of dark energy. Since voids are regions of low matter density, they may experience less gravitational resistance, allowing the expansion of space to occur more freely. If this is true, voids might act as accelerators for cosmic expansion, pushing galaxies apart at an even faster rate. The dipole repeller could be an example of this mechanism at work, offering a glimpse into how voids contribute to the overall structure of the cosmos. Another possibility is that voids interact with dark matter in unexpected ways. Dark matter, the invisible substance that makes up most of the universe's mass, is typically associated with galaxies and clusters. But what if dark matter is also present in voids, albeit in a more diffuse form? If so, it could play a role in shaping the gravitational landscape of these regions, further influencing the motion of galaxies. To investigate these ideas, astronomers are using a combination of observational data and sophisticated computer simulations. These simulations allow researchers to model the effects of voids on galactic motion, testing different scenarios to see which best matches real-world observations. By comparing these models to actual galaxy surveys, scientists can refine their understanding of how voids contribute to cosmic structure. If voids are found to be a major factor in cosmic motion, it could lead to a paradigm shift in astrophysics. Instead of viewing gravity as the primary force shaping the universe, we might need to consider the counteracting role of voids. This would require a fundamental rethinking of how cosmic expansion, galaxy formation, and dark energy interact. The study of the dipole repeller is still in its early stages, and many questions remain unanswered. What is the exact mechanism behind its repelling effect? Are other voids influencing galactic motion in similar ways? And could this discovery help us unlock the mysteries of dark energy and dark matter? As more data is collected, the answers to these questions will become clearer. But one thing is certain: the dipole repeller has already changed the way we think about the universe. It has revealed that voids are not just empty spaces but active participants in cosmic evolution. It has challenged our understanding of gravity, suggesting that the absence of matter can be just as influential as its presence. And it has opened up new avenues of research that could lead to groundbreaking discoveries in the years to come. The universe is vast and full of mysteries, but each new discovery brings us closer to understanding the forces that shape it. The dipole repeller is just one piece of a much larger puzzle, a glimpse into the hidden dynamics that govern cosmic motion. As we continue to explore the cosmos, we may find that the greatest mysteries are not found in the brightest galaxies or the densest clusters, but in the seemingly empty spaces between them. The realization that voids like the dipole repeller could be shaping the motion of galaxies as much as dense clusters is a fundamental shift in our understanding of cosmic structure. For centuries, astronomers have focused on gravity as the dominant force in shaping the universe. Galaxies cluster together because of their mutual gravitational attraction, forming superclusters and filaments that weave through the cosmos. But the dipole repeller suggests that the gravitational push from empty voids could be just as influential as the pull from massive galaxy clusters. This means that the large-scale motion of galaxies might be determined not only by what is there but also by what is missing. One of the most perplexing aspects of the dipole repeller is that it is an area of extremely low matter density, yet it seems to exert a powerful influence on the Milky Way and other nearby galaxies. This raises the question: how can an empty space have such a profound effect on cosmic motion? The answer lies in the nature of gravitational fields. In simple terms, galaxies tend to move away from underdense regions because there is less mass exerting gravitational attraction in those areas. Meanwhile, they are drawn toward overdense regions, where gravity is stronger. The result is a complex interplay of forces that shapes the motion of entire galaxy groups. Scientists have used detailed maps of the cosmic microwave background (CMB) radiation, the afterglow of the Big Bang, to track the large-scale motions of galaxies and identify the influence of structures like the dipole repeller. The CMB provides a reference point for measuring how galaxies move relative to the expansion of the universe. By analyzing the peculiar velocities of galaxies, motions that deviate from the uniform expansion of space, astronomers have been able to pinpoint the effect of both attractive and repulsive gravitational sources. The concept of void repulsion is not entirely new. In fact, computer simulations of large-scale cosmic structure have long suggested that voids should play an active role in shaping the motion of galaxies. However, the dipole repeller is the first concrete observational evidence that this effect is occurring on a massive scale in our local universe. This discovery has sparked renewed interest in the study of cosmic voids, prompting astronomers to investigate whether other voids exert similar repelling effects on galaxies. One of the main challenges in studying voids is that they are difficult to observe directly. Unlike galaxies and clusters, which shine brightly across the electromagnetic spectrum, voids are defined by their emptiness. This means that researchers must rely on indirect methods to study them, such as analyzing the distribution of galaxies and measuring their motion. Advanced mapping techniques, including redshift surveys and gravitational lensing studies, have provided valuable insights into the structure of voids and their role in cosmic evolution. As scientists continue to refine their understanding of the dipole repeller, they are also considering its implications for broader cosmological theories. One possibility is that voids could be linked to the mysterious force known as dark energy, which is driving the accelerated expansion of the universe. Some theories propose that voids could amplify the effects of dark energy, effectively acting as bubbles of accelerated expansion within the cosmic web. If true, this could provide important clues about the nature of dark energy and its influence on the universe. Another intriguing possibility is that voids might be shaped by the distribution of dark matter, the invisible substance that makes up most of the universe's mass. While dark matter is typically associated with galaxy clusters and filaments, it could also exist in more diffuse forms within voids. If dark matter is present in voids, it might interact with normal matter in unexpected ways, influencing the overall dynamics of cosmic motion. The discovery of the dipole repeller has also led astronomers to reconsider the way they classify cosmic structures. Traditionally, the focus has been on identifying large-scale galaxy clusters, superclusters, and filaments. But if voids are actively shaping the motion of galaxies, they should be treated as equally important components of the cosmic landscape. This shift in perspective could lead to a more comprehensive understanding of the forces that govern the universe. Future research on the dipole repeller and similar voids will rely on new observational data from upcoming space missions and advanced telescopes. Projects such as the Euclid mission, the Vera-C, Rubin Observatory, and the Square Kilometre Array will provide high-resolution maps of cosmic structure, allowing astronomers to study the distribution of matter and voids in unprecedented detail. These observations will help refine models of cosmic motion and improve our understanding of the role voids play in shaping the universe. One of the most exciting aspects of this research is that it could lead to entirely new discoveries about the nature of space itself. If voids are found to have unexpected properties, it might challenge existing theories of gravity and cosmic expansion. Some scientists have even speculated that voids could be linked to exotic physics, such as modifications to general relativity or the presence of unknown forces. While these ideas remain speculative, they highlight the potential for the dipole repeller to open new frontiers in cosmology. As we continue to explore the cosmos, the discovery of the dipole repeller serves as a reminder that the universe is full of surprises. It shows us that the forces shaping the motion of galaxies are more complex than we once thought, and that even the emptiest regions of space can play a crucial role in cosmic evolution. The study of voids is still in its early stages, but one thing is clear: the mysteries of the universe are far from solved. The more we learn about structures like the dipole repeller, the closer we come to understanding the true nature of the cosmos. The implications of the dipole repeller extend beyond just our local cosmic neighborhood. If voids like this are actively shaping the motion of galaxies, then they must be a key component of the large-scale structure of the universe. This realization challenges some long-standing assumptions in cosmology, and opens the door for new models that account for both attractive and repulsive gravitational forces. One of the biggest questions arising from the discovery of the dipole repeller is how many similar voids exist throughout the universe. If this effect is happening in our cosmic neighborhood, it is likely occurring elsewhere as well. The large-scale structure of the universe is often compared to a cosmic web, with galaxies and clusters forming dense filaments that weave through space, while vast empty voids make up the spaces in between. These voids are not uniform. Some are much larger and emptier than others. The dipole repeller might just be one of many repelling voids exerting an influence on galaxy motion. To investigate this possibility, astronomers are using increasingly sophisticated simulations to model how galaxies move over billions of years. These simulations, based on the fundamental laws of physics, attempt to recreate the observed distribution of galaxies and predict how voids might influence cosmic motion. Early results suggest that voids could play a more significant role than previously thought, not just in our local universe but across the entire observable cosmos. Another fascinating aspect of the dipole repeller is how it might relate to dark matter. While normal matter, stars, gas, and dust makes up only a small fraction of the universe's total mass, dark matter accounts for most of it. This invisible substance does not emit light or radiation, making it nearly impossible to detect directly. However, dark matter's presence is inferred through its gravitational effects on galaxies and cosmic structures. If voids like the dipole repeller are influencing galaxy motion, then dark matter must be playing a role in this process. One possibility is that the dipole repeller is not entirely empty, but instead filled with a diffuse distribution of dark matter. While galaxy clusters contain dense concentrations of dark matter, voids might have more spread out, low-density distributions. If dark matter interacts with normal matter in unexpected ways within these voids, it could create gravitational effects that enhance the repelling force observed in the dipole repeller. Some scientists are investigating whether certain properties of dark matter, such as its potential to clump or behave differently in low-density environments, could explain why voids seem to push galaxies away. Another possible explanation is tied to dark energy, the mysterious force responsible for the accelerated expansion of the universe. Some theories propose that voids could act as regions where dark energy is more dominant than in denser areas. Since dark energy is associated with repulsive forces on a cosmic scale, it is possible that voids amplify its effects, causing galaxies to move away from them at an accelerated rate. If this is true, voids could serve as natural laboratories for studying dark energy's influence on cosmic motion. To better understand the role of voids like the Dipole Repeller, astronomers are using advanced observational techniques to map the universe in greater detail. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey, are helping scientists create three-dimensional maps of cosmic structure. These maps allow researchers to trace the distribution of galaxies and voids, revealing patterns in how matter and empty space are arranged. In the coming years, new telescopes and space missions will provide even more detailed observations. The European Space Agency's Euclid mission, scheduled to survey billions of galaxies, aims to create the most comprehensive map of the universe's structure ever made. Similarly, the Vera C. Rubin Observatory will conduct the Legacy Survey of Space and Time, LSEST, capturing an unprecedented view of cosmic evolution. These projects will help confirm whether the Dipole Repeller is a unique anomaly or part of a larger pattern of void-induced cosmic motion. Beyond observational astronomy, physicists are exploring how the existence of voids like the Dipole Repeller could reshape our understanding of gravity itself. While Einstein's theory of general relativity has been incredibly successful at explaining the motion of galaxies and the expansion of the universe, some scientists believe it may not be the full picture. Alternative theories of gravity, such as modifications to general relativity, or new forces acting at cosmic scales, could provide a deeper explanation for why voids influence galaxy motion. Some researchers are investigating whether voids might reveal evidence of exotic physics, such as interactions between dark matter and dark energy that are not yet fully understood. If voids contain hidden properties that affect the way galaxies move, they could offer clues about fundamental forces that shape the cosmos. These ideas remain speculative, but they highlight how discoveries like the Dipole Repeller can lead to entirely new avenues of scientific exploration. Another major question is how voids like the Dipole Repeller evolve over cosmic time. The universe has been expanding for nearly 14 billion years, and cosmic structures have grown and changed throughout this period. Voids were once regions where matter was slightly less dense than average, but over billions of years, gravitational interactions have caused matter to move toward denser regions, making voids even emptier. This process, known as void evolution, means that voids have been getting larger and more defined over time. By studying the Dipole Repeller and similar voids, astronomers can learn more about how the universe's structure has developed from its early stages to the present day. If voids are actively shaping the motion of galaxies, they might have played a significant role in the formation of large-scale cosmic structures. Understanding their influence could help answer fundamental questions about how the universe took its current shape. The discovery of the Dipole Repeller has also raised philosophical questions about the nature of space and emptiness. In classical physics, empty space is often thought of as a passive backdrop, a void without influence. But the Dipole Repeller suggests that even nothingness can have a profound effect on the motion of galaxies. This challenges our perception of space itself, suggesting that emptiness is not just the absence of matter but an active player in cosmic dynamics. As scientists continue to investigate the Dipole Repeller, the broader implications of this discovery remain uncertain. Will we find more repelling voids shaping the motion of galaxies across the universe? Could these voids be linked to dark energy, dark matter, or even new physics? The answers to these questions could reshape our understanding of cosmology in ways we have yet to imagine. What is certain is that the Dipole Repeller is a reminder that the universe is far more complex than we once believed. While astronomers have spent centuries mapping the visible structures of the cosmos, this discovery highlights the importance of studying what is not there. The idea that vast empty spaces can shape the movement of entire galaxies is a humbling realization, one that forces us to rethink how the universe operates on its grandest scales. As new observations and theoretical models continue to refine our understanding of cosmic voids, the Dipole Repeller stands as a compelling example of how much we still have to learn. It is a testament to the power of scientific discovery, showing that even in the most unexpected places, where there appears to be nothing at all, we may find some of the universe's greatest mysteries. It is essential to consider how this discovery fits into the broader puzzle of cosmic motion. The movement of galaxies is dictated by a combination of forces, primarily gravitational attraction from massive structures and the expansion of the universe driven by dark energy. Yet, the realization that vast cosmic voids might be actively repelling galaxies introduces a new dimension to our understanding of large-scale cosmic flows. To appreciate the significance of this, we must revisit the fundamental forces at play. Gravity, as described by Einstein's general relativity, dictates that massive objects pull on one another, creating the web-like structure of the universe where galaxies cluster along filaments, separated by enormous voids. Historically, astronomers focused mainly on the role of these dense regions, galaxy clusters, superclusters, and massive structures such as the Great Attractor, which exerts a strong gravitational pull on the Milky Way and its neighbors. However, the discovery of the Dipole Repeller suggests that these motions are not simply a result of attraction but also repulsion. One of the most profound questions raised by the Dipole Repeller is whether it represents an isolated case or a general phenomenon governing cosmic motion. If voids across the universe are pushing galaxies away, this means that vast regions of empty space are shaping the universe's structure as much as the massive clusters of galaxies we usually focus on. This would imply a kind of dual mechanism. Galaxies are both being pulled by massive structures and simultaneously pushed away from empty voids. To test this idea, astronomers are employing powerful computational simulations that model the evolution of the universe over billions of years. These simulations start with the conditions present shortly after the Big Bang, and use the known laws of physics to predict how matter should distribute itself over time. What has become increasingly clear is that voids are not just passive regions of low density, they play an active role in shaping the cosmos. One reason for this is the concept of cosmic expansion. As the universe expands, matter tends to flow out of voids and into denser regions. This process, known as void evacuation, gradually empties voids of matter, amplifying their repelling effect. Over billions of years, voids become even more pronounced, creating stronger outflows of galaxies. The Dipole Repeller is one such region, where the large-scale movement of galaxies can be directly linked to the presence of an unusually empty void. However, this raises a deeper question: what exactly makes the Dipole Repeller such a strong repelling force? If voids generally push matter away, why is this one particularly significant? The answer may lie in the way dark matter and dark energy interact in these regions. Dark matter, the mysterious substance that makes up most of the universe's mass, does not emit or reflect light, but it exerts a strong gravitational pull. Some researchers propose that the Dipole Repeller may not be a completely empty void, but rather a region with a unique dark matter distribution. If dark matter behaves differently in voids, perhaps spreading out more thinly than expected, it could create a repelling effect stronger than previously thought. Another possibility is that dark energy, which drives the accelerated expansion of the universe, might be more concentrated in voids than in denser regions. If dark energy exerts a repulsive force, then voids like the Dipole Repeller could act as natural accelerators, pushing galaxies away at an even greater rate. This would mean that voids are not just passive gaps in the cosmic web but active regions where the fundamental forces of the universe behave in unexpected ways. Understanding this process requires detailed observational data, and this is where upcoming astronomical surveys will play a crucial role. The European Space Agency's Euclid mission, for example, aims to map the distribution of galaxies and dark matter with unprecedented precision. Similarly, the Vera C. Rubin Observatory's upcoming Sky Survey will track the motion of millions of galaxies, helping to determine whether other repelling voids exist beyond the Dipole Repeller. If similar repelling voids are found across the universe, it would mark a significant shift in our understanding of cosmic motion. It would mean that voids are not merely the absence of matter but dynamic structures with real, measurable effects on galaxy movement. This would also raise intriguing questions about the fundamental nature of space itself. For centuries, space has been thought of as an empty backdrop, a stage upon which galaxies and stars play out their cosmic dance. But what if space itself has structure? What if the vast, empty voids of the universe are not just gaps in the cosmic web but active players in the universe's evolution? The discovery of the dipole repeller suggests that what we consider empty may, in fact, be shaping the fate of entire galaxies. This concept challenges our traditional understanding of gravity. If voids can push as effectively as clusters pull, then our current models of cosmic motion may need to be revised. Some physicists speculate that this could hint at modifications to general relativity, suggesting that the nature of gravitational interactions may be more complex than Einstein's equations describe. Others propose that the dipole repeller could be evidence of interactions between dark matter and dark energy that we have yet to understand. What makes this discovery even more exciting is that it provides a rare opportunity to test these ideas. Unlike many theoretical concepts in physics that remain purely speculative, the dipole repeller is a real, observable phenomenon. Its effects on the motion of galaxies can be measured, allowing astronomers to develop new models that explain its influence. As research continues, one thing is clear: the dipole repeller is not just a minor anomaly, it is a gateway to deeper questions about the universe. It forces us to reconsider the role of emptiness, the nature of cosmic flows, and the fundamental forces that shape the cosmos. It challenges our assumptions and opens the door to new discoveries that could reshape our understanding of space, time, and gravity itself. Ultimately, the dipole repeller serves as a reminder that the universe is still full of mysteries. Even in the vast emptiness of space, forces are at work that we are only beginning to comprehend. What seems like nothingness may, in fact, hold the key to some of the biggest unanswered questions in cosmology. And as astronomers continue to probe the depths of space, there is no telling what other secrets the universe has yet to reveal. The discovery of the dipole repeller does more than just challenge our understanding of cosmic motion. It forces us to rethink the very structure of the universe. If voids like the dipole repeller actively push galaxies away, then these empty regions are not passive gaps in the cosmic web but dynamic players in shaping the large-scale universe. This realization raises a number of intriguing questions, some of which could change the way we view gravity, dark energy, and even the fabric of space itself. One of the most pressing questions is, what exactly causes the repelling effect of the dipole repeller? The simplest explanation is that it is a result of the gravitational balance between overdense and underdense regions. The universe is not uniform. Matter clumps together in some areas while other regions remain relatively empty. These voids expand over time as matter moves toward denser areas, creating the illusion that galaxies are being pushed away from them. But could there be something more at play? Some physicists speculate that the dipole repeller could provide evidence for modifications to our understanding of gravity. Einstein's general relativity describes gravity as a curvature of spacetime, and so far, all observational data supports this framework. However, some alternative theories suggest that gravity might behave differently on cosmic scales, leading to effects that resemble repulsion. One such possibility is a phenomenon known as modified gravity, where the laws of gravity change at very large distances. Some versions of these theories suggest that gravity weakens more than expected at vast cosmic scales, causing matter to be pushed outward from voids more strongly than standard models predict. This could explain why the dipole repeller has such a pronounced effect on the Milky Way's motion. Another possibility involves the mysterious force known as dark energy. Dark energy is responsible for the accelerated expansion of the universe, but its exact nature remains unknown. Some researchers propose that dark energy is not evenly distributed throughout space but instead accumulates in voids. If true, then voids like the dipole repeller could be regions where dark energy's repulsive force is particularly strong, creating an additional outward push on galaxies. Observationally, one of the most intriguing aspects of the dipole repeller is how its influence was detected. Unlike direct observations of galaxies or cosmic structures, The dipole repeller was identified through the study of cosmic flows, the large-scale movement of galaxies across space. By carefully mapping the velocities of thousands of galaxies, astronomers noticed a consistent pattern. Galaxies were not just moving toward known attractors like the Shapley supercluster, but were also accelerating away from a specific empty region. This was the first major clue that something beyond simple gravitational attraction was influencing cosmic motion. This method of mapping cosmic flows has since been applied to other parts of the universe, revealing additional voids that might have similar repelling effects. If more dipole repeller-like voids are found, it could confirm that these repelling forces are not unique but a fundamental aspect of cosmic structure. This would provide strong evidence that voids are just as important in shaping the universe as massive galaxy clusters. One of the most exciting aspects of this discovery is how it fits into the broader study of cosmic voids. For decades, astronomers have primarily focused on dense regions of the universe, galaxy clusters, filaments, and superclusters, because these are the most easily observable structures. But in recent years, there has been growing interest in voids, leading to new insights about how the universe evolves. For example, studies have shown that galaxies inside voids evolve differently from those in denser regions. Because voids are relatively isolated, the galaxies within them experience fewer interactions and collisions compared to galaxies in clusters. This means that void galaxies tend to be less massive, have slower star formation rates, and contain more pristine gas that has not been processed through multiple generations of stars. Understanding how these galaxies evolved could provide important clues about the early universe and the conditions that led to the formation of the first galaxies. The study of voids has also led to new ways of testing cosmological theories. Since voids are some of the largest and emptiest structures in the universe, they provide an excellent laboratory for studying dark energy. By measuring how voids expand over time, astronomers can place constraints on different models of dark energy, helping to determine whether it behaves as a constant force or changes over time. If dark energy is stronger in voids, as some theories suggest, then voids like the dipole repeller could hold the key to understanding one of the greatest mysteries in physics. Beyond dark energy, voids could also offer insights into the nature of dark matter. While dark matter is usually associated with dense regions like galaxy clusters, it also plays a crucial role in shaping voids. Some models suggest that voids might contain a different distribution of dark matter than previously thought, with subtle effects on cosmic expansion. Studying these effects could provide valuable clues about the properties of dark matter and how it interacts with normal matter. Looking ahead, upcoming telescopes and observational projects will play a crucial role in deepening our understanding of cosmic voids and their effects. The Vera C. Rubin Observatory, set to begin operations in the near future, will conduct an extensive survey of the sky, tracking the motion of billions of galaxies. This will allow astronomers to map cosmic flows with unprecedented precision, potentially revealing more repelling voids like the dipole repeller. Similarly, the European Space Agency's Euclid mission aims to create a detailed 3D map of the universe, tracing the distribution of dark matter and dark energy across cosmic time. By comparing Euclid's data with existing cosmic flow maps, researchers will be able to refine their models of how voids influence galaxy motion. If these studies confirm that voids exert a significant repelling force, it would mark a major shift in our understanding of the cosmos. It would mean that the universe is not simply a battle between gravitational attraction and dark energy-driven expansion, but also a dynamic interplay between dense structures pulling galaxies in and vast voids pushing them away. The implications of this discovery extend beyond cosmology. If voids play a significant role in shaping the universe, it could have consequences for other areas of physics, including quantum mechanics and the nature of space-time itself. Some speculative theories suggest that voids could be connected to unknown physical processes that influence the large-scale structure of the universe. Ultimately, the dipole repeller serves as a powerful reminder that the universe is still full of surprises. Even in the vast emptiness of space, there are forces at work that we are only beginning to understand. What appears to be nothingness may, in fact, be one of the most important factors shaping the cosmos. As astronomers continue to probe deeper into the nature of voids, the Dipole Repeller may be just the first of many discoveries that challenge our understanding of the fundamental forces governing the universe. With each new observation, we move closer to unraveling one of the greatest mysteries of cosmology: how the universe came to be the way it is, and what role these hidden forces play in its evolution. And as we continue to map the unseen influences shaping our galaxy's motion, one thing is clear: the Dipole Repeller is only the beginning of a much larger story. The discovery of the Dipole Repeller is just one piece of a much larger cosmic puzzle. It suggests that the universe is not merely a battle between gravitational attraction and dark energy-driven expansion, but a complex interplay of forces, where vast cosmic voids act as silent yet powerful players in shaping galactic motion. But what if the Dipole Repeller is not alone? What if there are more such repelling regions across the cosmos, each exerting an unseen influence on the structure and movement of galaxies? The idea that voids could have a repelling effect is not entirely new, but until the discovery of the Dipole Repeller, it was largely theoretical. Traditionally, cosmologists viewed voids as passive gaps in the cosmic web, regions where matter simply never accumulated. But the Dipole Repeller suggests that these voids are not just empty spaces. They are actively shaping the universe in ways we are only beginning to understand. If this is true, then mapping cosmic voids could become just as important as studying galaxy clusters when it comes to understanding the large-scale structure of the universe. One major question that remains unanswered is whether the Dipole Repeller is unique. If it is, then it may simply be an unusual feature of our local cosmic neighborhood. But if similar repelling voids exist throughout the universe, then we may have to rethink our entire approach to cosmology. Future surveys, such as those being conducted by the Vera C. Rubin Observatory and the Euclid mission, will help answer this question by mapping more of the cosmic web in greater detail. If multiple repelling voids are found, it could have profound implications for our understanding of gravity. One of the biggest mysteries in physics today is whether Einstein's general relativity is the final word on gravity, or whether it needs to be modified at cosmic scales. Most of the universe's mass is made up of dark matter, an invisible substance that only interacts through gravity, and dark energy, the unknown force driving cosmic acceleration. If voids like the Dipole Repeller exert a stronger than expected repelling effect, it could be a sign that our models of gravity need to be adjusted. Some physicists propose that cosmic voids could be testing grounds for alternative theories of gravity, such as modified Newtonian dynamics, MOND, or F.R. gravity, which suggests that the force of gravity behaves differently at vast cosmic scales. If such theories turn out to be correct, it would rewrite our understanding of fundamental physics, possibly even leading to new insights into the nature of dark matter and dark energy. Beyond gravity, the Dipole Repeller also raises questions about the role of dark energy in cosmic expansion. Dark energy is often described as a uniform force that permeates all of space, but what if it is not evenly distributed? Some theories suggest that dark energy could accumulate in cosmic voids, creating regions of higher repelling force. If true, then voids could be hotspots of dark energy activity, meaning that the repelling force of the Dipole Repeller may not be entirely due to gravitational effects alone. This could explain why the Milky Way is being pushed so strongly in a particular direction. If the void that forms the Dipole Repeller contains a higher concentration of dark energy, then it may be acting like a giant cosmic pressure zone, pushing everything around it outward. This would be a groundbreaking discovery, as it would provide direct observational evidence that dark energy is not uniform but instead varies across different regions of space. One of the challenges in studying cosmic voids is that they are, by definition, difficult to observe. Since they contain very few galaxies, traditional telescopic surveys struggle to gather data from these regions. However, new techniques are being developed to study voids using the cosmic microwave background (CMB), the afterglow of the Big Bang. By analyzing how light from the CMB is distorted as it passes through cosmic voids, astronomers can infer the presence of dark matter, dark energy, and even potential repelling forces. Another promising method is the study of gravitational lensing, where the light from distant galaxies is bent by the gravitational influence of massive structures. While lensing is usually used to study dense regions like galaxy clusters, it can also be used to study voids by looking at how light subtly changes as it moves through empty space. If voids exert a repelling effect, this could be detectable through precise gravitational lensing measurements. Looking further ahead, advances in artificial intelligence and machine learning are expected to play a major role in analyzing cosmic voids. The sheer amount of data being collected by modern telescopes is overwhelming, and AI algorithms are increasingly being used to sift through this data, identifying patterns that might be missed by human researchers. If AI can detect subtle signatures of repelling forces in voids, it could lead to a new way of classifying and understanding cosmic structures. The implications of all this research extend beyond cosmology. If voids are actively influencing galaxy motion, then they may also play a role in galaxy evolution. Galaxies that form near voids may experience different evolutionary paths compared to those in denser regions, leading to variations in star formation rates, chemical compositions, and even the formation of supermassive black holes. Understanding these effects could help astronomers answer some of the biggest questions about how galaxies, including our own, came to be. The Dipole Repeller is just the beginning of a new era in astrophysics. It challenges our assumptions about the universe, forcing us to reconsider the balance of forces that shape cosmic structure. Whether it turns out to be an isolated phenomenon or part of a larger pattern, one thing is clear: the universe is far more dynamic and mysterious than we ever imagined. As we continue to explore the cosmos, new discoveries will undoubtedly emerge, each one reshaping our understanding of space and time. The Dipole Repeller is a reminder that even in the vast emptiness of space, unseen forces are at work, influencing the motion of galaxies, shaping the cosmic web, and perhaps even hinting at new physics waiting to be uncovered. The discovery of the Dipole Repeller is not just a revelation about cosmic motion, it is a paradigm shift in how we understand the structure of the universe itself. For decades, astronomers focused primarily on regions of high matter density, assuming that galaxy clusters and superclusters dictated the gravitational flow of the cosmos. But the Dipole Repeller challenges this perspective. It suggests that voids, previously thought to be passive gaps in the cosmic web, might actively influence the universe's large-scale dynamics. This realization has profound implications for cosmology. If voids exert a repelling force, then they must play a critical role in shaping the distribution of galaxies over cosmic time. This means that our current models of structure formation, which focus on gravitational attraction alone, may be incomplete. It also suggests that the large-scale flow of galaxies is not just a one-way attraction toward dense regions but a two-way push-pull interaction between attractors and repellers. But what exactly is causing this repelling effect? The most straightforward explanation is gravitational imbalance. The Dipole Repeller is located in an underdense region of space, meaning that galaxies in our local universe are gravitationally pulled away from it and toward denser areas, such as the Shapley supercluster. This movement creates the illusion of a repelling force, even though it is actually the result of gravitational attraction elsewhere. However, some researchers have speculated that there could be more at play. One possibility is that the Dipole Repeller is not just a void but an active agent in the cosmic expansion. If certain regions of space contain higher concentrations of dark energy, they might exert a genuine repelling force, pushing matter away rather than simply being ignored by gravity. This would mean that voids are not just passive regions but dynamic components of the cosmic landscape. If this theory is correct, it could help solve one of the biggest mysteries in physics: the nature of dark energy. Dark energy is currently understood as a uniform force that drives the accelerated expansion of the universe. But what if it is not evenly distributed? If dark energy accumulates in voids, it could create local zones of stronger repelling effects, meaning that cosmic expansion is not happening at a constant rate everywhere but instead varies depending on the distribution of dark energy. This could explain why the Milky Way and other nearby galaxies are being pushed with such force. If the Dipole Repeller contains a higher-than-average concentration of dark energy, then it could be acting like a giant cosmic pressure zone, repelling everything around it. This would be a groundbreaking discovery because it would provide observational evidence that dark energy is not uniform but instead clusters in specific regions. The challenge, however, is proving this idea. Since dark energy does not emit light or interact with normal matter in a detectable way, astronomers must rely on indirect methods to study it. One possible approach is to look for subtle distortions in the cosmic microwave background radiation, the afterglow of the Big Bang. If dark energy is concentrated in voids, it could leave a faint imprint on this radiation, altering its temperature and polarization patterns. Another way to investigate the dipole repeller is through large-scale galaxy surveys. By mapping the positions and velocities of millions of galaxies, astronomers can reconstruct the flow of matter in the universe and identify other potential repelling regions. If similar voids with strong repelling effects are found elsewhere, it would provide strong evidence that the dipole repeller is not unique but part of a larger cosmic phenomenon. Additionally, upcoming space missions, such as the Euclid Telescope and the Vera C. Rubin Observatory, will provide high-resolution maps of the cosmic web, allowing scientists to study voids in unprecedented detail. These missions will help determine whether the dipole repeller is an isolated feature or part of a broader pattern that affects the entire universe. If multiple repelling voids are discovered, it could mean that our current understanding of cosmology needs to be revised. It would suggest that the universe is shaped not only by gravitational attraction but also by an intricate balance of forces, with voids playing a more active role than previously thought. This could lead to new theories of gravity that extend beyond Einstein's general relativity, possibly even providing clues about the true nature of dark matter and dark energy. Beyond its scientific implications, the dipole repeller also raises philosophical questions about our place in the universe. If our galaxy's movement is being influenced by an unseen force in a vast cosmic void, it challenges the way we perceive our cosmic neighborhood. It reminds us that the universe is not a static, unchanging entity, but a dynamic and evolving system, shaped by forces we are only beginning to understand. This discovery also has implications for the future of space exploration. If voids exert a repelling effect, then intergalactic travel may be more complex than we imagine. If spacecraft are ever able to travel beyond our galaxy, they may need to navigate not just gravitational wells but also repelling zones that could alter their trajectories. Understanding these forces could be crucial for plotting courses through the vast cosmic ocean. The dipole repeller is a mystery that continues to challenge our understanding of the cosmos. Whether it is a mere gravitational anomaly or a sign of new physics, it has already reshaped our view of the universe. As we continue to explore the cosmos, new discoveries will undoubtedly emerge, each one challenging our assumptions and revealing new layers of complexity in the fabric of space and time. The implications of the dipole repeller extend far beyond just understanding the motion of the Milky Way. This discovery forces us to reconsider fundamental questions about how the universe is structured and how it evolves over time. Traditionally, the study of cosmic flows has focused on massive structures like galaxy clusters, assuming that the gravitational pull of these dense regions dictates the large-scale motion of galaxies. But the dipole repeller suggests that vast, empty voids also play an active role in shaping the cosmic landscape. This idea is not entirely new. The concept that underdense regions could contribute to cosmic flows has been explored in theoretical models, but the dipole repeller provides the first strong observational evidence that voids are not merely passive gaps in the cosmic web. Instead, they appear to be dynamic structures that influence the movement of galaxies in a way that was previously underestimated. One of the most intriguing aspects of the dipole repeller is its potential connection to dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, but its exact nature remains one of the biggest unanswered questions in physics. If voids like the dipole repeller contain higher concentrations of dark energy, they might be responsible for localized repelling effects, pushing galaxies away from these regions. This would challenge the traditional view that dark energy is evenly distributed throughout the universe, and instead suggest that it clusters in specific locations. If this hypothesis is correct, it would have profound implications for our understanding of cosmic expansion. It would mean that the rate of expansion is not uniform across the universe but instead varies depending on the distribution of dark energy. This could help explain why some galaxies appear to be moving faster than others and why certain regions of the universe have different large-scale structures. To test this idea, astronomers are looking for additional evidence of repelling voids. If other regions similar to the dipole repeller exist, it would support the idea that cosmic expansion is influenced by a balance of gravitational attraction and repelling forces. Large-scale surveys of the universe, such as those conducted by the Sloan Digital Sky Survey (SDSS), and upcoming missions like Euclid, are providing increasingly detailed maps of cosmic structures. These maps will allow researchers to analyze the movement of galaxies with greater precision and identify potential patterns in their motion. Another approach to studying the dipole repeller is through computer simulations. By creating models of the universe that include both attractive and repelling forces, scientists can test different scenarios and see which ones best match observational data. If simulations that incorporate repelling voids provide a better fit to real-world observations, it would strengthen the case for the dipole repeller being a genuine cosmic phenomenon rather than just a statistical anomaly. One of the challenges in understanding the dipole repeller is the difficulty of observing voids directly. Since these regions contain very little matter, they do not emit light or radiation in the way that galaxies or galaxy clusters do. This makes them difficult to detect with traditional telescopes. However, indirect methods, such as measuring the velocities of galaxies and analyzing their motion patterns, provide valuable clues about the presence and influence of these voids. The dipole repeller also raises questions about the overall structure of the universe. The standard model of cosmology describes the universe as a vast cosmic web, with galaxies and galaxy clusters forming the long filaments that connect to large superclusters. These structures are thought to be shaped primarily by dark matter and the gravitational interactions between galaxies. However, if voids play an active role in shaping cosmic motion, then they must be incorporated into our models of large-scale structure formation. This means that the standard picture of the universe as a network of galaxy clusters pulling matter toward them may need to be revised to include a more dynamic interplay between attraction and repulsion. It could also mean that the distribution of dark matter and dark energy is more complex than previously thought. If voids are actively pushing galaxies away, they could be revealing new properties of these mysterious components of the universe. Beyond the scientific implications, the dipole repeller also has philosophical and existential significance. It highlights how much we still have to learn about the universe, and how even seemingly empty regions of space can hold deep mysteries. The fact that our galaxy, and by extension, our entire cosmic neighborhood, is being influenced by an unseen force in deep space is a humbling reminder of how small and interconnected we are within the vast expanse of the cosmos. This discovery also raises new questions about the ultimate fate of the universe. If repelling forces exist on large scales, they could play a role in determining how the universe evolves over time. Will the repelling effects of voids become stronger as the universe continues to expand? Could they contribute to a future scenario in which galaxies are pushed apart so forcefully that the cosmic web itself unravels? These are questions that scientists are only beginning to explore, and the answers could reshape our understanding of the cosmos in profound ways. For now, the dipole repeller remains a mystery, but it is one that astronomers are determined to unravel. As new telescopes and observational techniques continue to improve, we may soon have a clearer picture of what is driving this cosmic motion. Whether it is purely a gravitational effect, a manifestation of dark energy, or something even more exotic, the dipole repeller represents a frontier in our quest to understand the universe. As we continue to probe the depths of space, discoveries like the dipole repeller remind us that the cosmos is full of surprises. Every answer leads to new questions, and every mystery we solve brings us closer to understanding the fundamental forces that shape our reality. The journey to uncover the true nature of the universe is far from over, and the dipole repeller is just one of many cosmic enigmas waiting to be fully understood. The discovery of the dipole repeller challenges some of our longest-standing assumptions about how galaxies move through the universe. For decades, astronomers have relied on the principle that gravity is the primary force shaping the large-scale cosmic structures. This assumption led to the idea that the motion of galaxies is largely dictated by the gravitational pull of massive structures such as galaxy clusters and superclusters. However, the existence of a repelling force, one that appears to push galaxies away from certain regions, suggests that our understanding of cosmic flows may be incomplete. One of the biggest questions that arise from the dipole repeller's influence is, what exactly is causing this repelling effect? The prevailing explanation is that the dipole repeller is an underdense region, meaning that it contains fewer galaxies and less matter than the surrounding areas. Because matter has gravitational pull, regions with less matter exert less of this pull, creating what is effectively a gravitational void. In simple terms, galaxies are drawn toward denser regions while simultaneously being pushed away from these voids. This interplay between attraction and repulsion shapes the motion of galaxies across vast cosmic distances. The presence of such an influential underdense region reinforces the importance of cosmic voids in the large-scale structure of the universe. Voids are among the most mysterious structures in cosmology. Unlike galaxy clusters, which are relatively easy to observe due to their high concentration of stars and matter, voids are dark, empty regions that contain very little visible matter. Despite this, they play a critical role in the evolution of the universe. These voids are not merely passive gaps between galaxies. They actively shape the movement of cosmic structures. The dipole repeller is an extreme example of how voids can influence galactic motion on a grand scale. Scientists are now investigating whether the dipole repeller is a unique anomaly or if similar repelling voids exist elsewhere in the universe. If other repelling voids are found, it would suggest that these structures are a fundamental component of the cosmic web, influencing the motion of galaxies in ways we have only begun to understand. Some researchers speculate that cosmic voids might even be linked to dark energy, the mysterious force driving the acceleration of the universe's expansion. Dark energy remains one of the greatest mysteries in modern physics. It is widely believed to make up about 68% of the total energy in the universe, yet its nature is still unknown. One intriguing hypothesis is that dark energy is not evenly distributed but rather concentrates in specific regions, including voids like the dipole repeller. If true, this could help explain why voids appear to push galaxies away. Instead of merely being regions of low matter density, they could be reservoirs of repelling energy, exerting an anti-gravitational effect on surrounding galaxies. To test this hypothesis, astronomers are conducting deep space surveys to map the distribution of galaxies and cosmic voids with greater precision. Projects like the Dark Energy Survey (DS) and the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time (LSST) aim to create detailed three-dimensional maps of the universe's structure. By tracking how galaxies move relative to both dense and underdense regions, researchers hope to uncover new insights into the nature of cosmic repulsion. Computer simulations are also playing a key role in exploring the impact of repelling voids. By modeling the universe with different assumptions about dark energy, gravitational attraction, and void dynamics, scientists can compare their simulations to actual observational data. If models that incorporate repelling voids provide a better match to real-world galaxy motion, it would lend support to the idea that voids are not just empty spaces but active participants in cosmic evolution. The implications of the dipole repeller extend beyond astrophysics. This discovery forces us to reconsider how forces in the universe interact on the largest scales. If the universe is governed by both attractive and repelling forces, it may mean that our understanding of fundamental physics is incomplete. Some researchers speculate that repelling voids could be related to modifications of Einstein's theory of general relativity. If gravity behaves differently in extremely underdense regions, it could open the door to new physics beyond our current models. Another possibility is that repelling voids could be linked to exotic forms of matter or energy that have yet to be discovered. Some theories suggest that there could be unknown particles or forces that interact with galaxies in ways we do not yet understand. If voids like the dipole repeller contain these unknown elements, they could provide crucial clues about the nature of dark matter, dark energy, or even entirely new physics. The study of the dipole repeller also has broader implications for our understanding of the ultimate fate of the universe. If repelling voids play a significant role in cosmic expansion, they could contribute to scenarios in which the universe's growth accelerates indefinitely. Some cosmologists have proposed that in a far distant future, galaxies may be pushed so far apart that they become isolated from one another, leading to a scenario known as the Big Freeze, or heat death, where the universe continues expanding until all matter is spread too thin to sustain stars and galaxies. Alternatively, if voids contain concentrated pockets of dark energy, they might create localized expansion effects that could lead to more complex cosmic evolution scenarios. Some models suggest that regions of the universe could expand at different rates, leading to the formation of isolated cosmic bubbles that evolve independently of one another. If this is the case, the dipole repeller could be a small part of a much larger and more intricate cosmic landscape than we currently imagine. Beyond these scientific implications, the dipole repeller reminds us of how much we still have to learn about the cosmos. The fact that our galaxy is being influenced by a vast, invisible force millions of light years away underscores how interconnected the universe truly is. Even though we are just beginning to understand the dipole repeller, its discovery represents a crucial step in unraveling the mysteries of large-scale cosmic motion. As our technology improves, we will likely find more evidence of cosmic repulsion and its role in shaping the universe. Future telescopes, such as the James Webb Space Telescope and next-generation observatories, will provide even more detailed data on cosmic structures. These advancements may eventually lead us to a breakthrough in understanding how galaxies move, how voids interact with dark energy, and how the universe itself evolves over time. The dipole repeller is a testament to the complexity of the cosmos and the never-ending quest for knowledge. It challenges us to think beyond traditional models and embrace the possibility that the universe is shaped by forces we are only beginning to comprehend. Whether it ultimately leads to new discoveries about dark energy, modified gravity, or even unknown cosmic forces, one thing is certain: the dipole repeller is just the beginning of a much larger cosmic mystery that will continue to intrigue scientists and space enthusiasts alike for generations to come. If the dipole repeller is just one example of a large-scale cosmic void influencing galactic motion, then it raises an even bigger question: how many of these repelling forces exist across the universe? Could the cosmos be filled with a network of massive voids, each subtly nudging and shaping the paths of entire galaxies? The idea that our Milky Way is not just being pulled toward dense regions but also pushed away from underdense ones suggests that the entire cosmic web is in a delicate and dynamic balance, constantly shifting due to invisible forces we have only recently begun to detect. This changes the way we think about galactic movement. Traditionally, we assumed that the biggest, densest structures, like galaxy clusters, were the sole drivers of cosmic motion. The discovery of the dipole repeller suggests that voids are just as important, if not more so in some cases. If that's true, then the large-scale structure of the universe isn't just about where matter is concentrated, it's also about where matter is missing. To put this into perspective, imagine a cosmic tug-of-war. On one side, enormous superclusters, like the Shapley supercluster, which exerts a powerful gravitational pull, are pulling galaxies toward them. But on the other side, massive voids, like the dipole repeller, are pushing galaxies away. The motion of the Milky Way and countless other galaxies isn't just the result of being pulled in one direction. It's the result of being simultaneously pushed and pulled in a cosmic ballet that spans billions of light years. But what makes the dipole repeller so fascinating is that it's not just any void. It appears to be one of the most influential voids ever discovered. The sheer scale of its effect suggests that it could be one of the largest known underdense regions, possibly extending hundreds of millions of light years across. If that's the case, then its influence on the motion of the Milky Way, and countless other galaxies, could be even greater than we currently estimate. The existence of the dipole repeller also raises new questions about the nature of voids themselves. What if cosmic voids aren't just empty spaces but rather regions with unique physical properties that we don't yet understand? Some physicists have speculated that voids could be shaped by exotic physics, such as interactions between dark energy and dark matter. Since dark energy is believed to be responsible for the accelerating expansion of the universe, some theories suggest that it could be more concentrated in voids, creating a stronger repelling effect than previously assumed. This leads to an even more mind-bending possibility. What if voids like the Dipole Repeller are actually manifestations of a deeper cosmic phenomenon that we have yet to fully grasp? Some physicists have proposed that voids could be connected to the mysterious concept of the cosmic inflation field, the force that caused the rapid expansion of the universe in its earliest moments. If voids are linked to remnants of this primordial expansion, they could hold crucial clues about the nature of the universe's birth and its ultimate fate. Another possibility is that the Dipole Repeller's repelling effect isn't solely due to its lack of matter but also to the presence of unknown cosmic structures within it. Some researchers have speculated that voids could contain hidden, exotic objects, such as large-scale quantum fluctuations, unseen dark matter structures, or even unknown forms of energy that have yet to be detected. If that's the case, then the Dipole Repeller might not just be an empty void but rather a region of the universe where entirely new physics is at play. The impact of this discovery extends beyond just theoretical physics. If voids like the Dipole Repeller play a major role in galactic movement, then it could change the way we model the future evolution of the universe. Right now, our best cosmological models rely on the assumption that galaxies move primarily due to gravitational attraction. If repelling voids turn out to be a significant factor, then those models may need to be revised. For instance, if voids exert a greater repelling force than we thought, then it's possible that the universe's expansion could be even more complex than we currently assume. Some scientists have speculated that if voids continue to push galaxies apart, they could contribute to an uneven expansion pattern, leading to regions of space that expand at different rates. This could mean that different parts of the universe could evolve in dramatically different ways over the next billions of years. One of the most unsettling possibilities is that repelling voids could eventually separate galaxies so far apart that they become completely isolated from one another. This could accelerate the so-called Big Freeze scenario, in which the universe expands so much that galaxies become isolated islands in an ever-expanding void, eventually fading into darkness as stars burn out and new ones fail to form. If voids like the Dipole Repeller continue to push galaxies apart, they could play a key role in this cosmic endgame. But before we get too far ahead of ourselves, there's still so much we don't know about the Dipole Repeller. For now, astronomers are working to map its exact shape, size, and influence with greater precision. The more we learn about it, the more we may uncover about the hidden forces shaping our universe. With upcoming observational projects, like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, we'll have even better tools to investigate these vast cosmic voids. One thing is clear: the Dipole Repeller is just the beginning of a much larger mystery. It has already forced us to rethink how galaxies move, how voids shape the cosmos, and what forces might be at play beyond gravity itself. It reminds us that the universe is still full of surprises, and that some of the biggest discoveries might come not from what we see, but from what we don't. The Dipole Repeller is just one example of a hidden force in the universe. But if it has this much influence over the Milky Way, how many other unseen repellers might be out there? Could there be an entire network of cosmic voids that act like invisible walls, shaping the very structure of the universe in ways we have yet to fully grasp? For a long time, cosmologists believed that the large-scale structure of the universe was primarily shaped by gravity. Galaxies were thought to be moving because of the pull of massive clusters, the attractive force of dark matter, and the slow expansion caused by dark energy. But the Dipole Repeller introduces a new factor into this equation, one that suggests that empty space itself might play a more active role than we ever imagined. If voids are not just passive gaps between galaxies but active regions that push matter away, then we might need to reconsider how the cosmic web is structured. We already know that galaxies tend to form along vast filaments of matter, with immense voids separating them. But what if these voids are not just empty regions but dynamic forces that influence the direction of galactic motion? What if the entire universe is engaged in a constant push and pull dance, where both attraction and repulsion shape its evolution? This could change how we predict the long-term fate of the cosmos. If the expansion of the universe is influenced by a combination of gravitational attraction and void repulsion, then the way galaxies spread apart over billions of years might be more complex than we currently assume. Some regions of the universe might experience accelerated expansion due to the presence of large repelling voids, while others might remain more stable due to the gravitational pull of dense clusters. In fact, some scientists have speculated that the presence of massive voids like the Dipole Repeller could explain certain anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang that provides a snapshot of the early universe. There are certain cold spots in this radiation that have puzzled cosmologists for years. Some researchers believe these cold spots might be the remnants of enormous voids that have influenced the structure of the universe since its infancy. If that's true, then the Dipole Repeller might not just be an isolated phenomenon. It could be part of a much larger cosmic pattern that extends back to the earliest moments of existence. But let's take this idea even further. If voids are shaping the motion of galaxies, could they also be shaping the distribution of dark matter itself? Dark matter is one of the greatest mysteries in physics. It makes up most of the mass in the universe, yet we cannot see or directly detect it. It only reveals itself through its gravitational effects on galaxies. But if voids like the Dipole Repeller are exerting a repelling force, could they also be influencing the way dark matter is arranged in the cosmic web? Some theories suggest that dark matter might be even more sensitive to the presence of voids than regular matter. Since dark matter doesn't interact with light or normal particles in the same way, it could be influenced by void repulsion in a way we don't yet understand. This could mean that voids play a crucial role in the overall structure of the universe, not just by shaping the movement of galaxies, but by determining where dark matter itself is concentrated. And if that's true, then understanding the Dipole Repeller could be a key to unlocking one of the biggest unsolved questions in physics. What exactly is dark matter? If we can understand how voids interact with dark matter, we might be able to detect subtle clues about its nature. Is dark matter made up of yet undiscovered particles? Could it be interacting with voids in ways that reveal new physics? Could the Dipole Repeller be providing us with a rare glimpse into the unseen forces that shape reality itself? But there's another mystery tied to the idea of repelling voids. What role does dark energy play in all of this? Dark energy is the force responsible for the accelerating expansion of the universe, and it remains one of the greatest puzzles in cosmology. Some scientists have speculated that voids might be linked to dark energy in a way we don't yet fully grasp. If voids are more than just empty spaces, if they are regions where dark energy is concentrated, then the Dipole Repeller could be a direct manifestation of dark energy at work. This would mean that voids are not just passive gaps between galaxies, but active regions that push matter apart due to the influence of dark energy. This could be a crucial missing piece in our understanding of the universe's expansion. One radical idea is that voids could act as dark energy wells, places where dark energy pulls and exerts a stronger repelling force. If this is the case, then the Dipole Repeller might not just be a random underdense region, but a key part of a much larger cosmic mechanism that governs the fate of the universe. This could also explain why the Milky Way is moving at the speed that it is. If the Dipole Repeller is pushing us away, and dense clusters like the Shapley supercluster are pulling us in, then the combined effect of attraction and repulsion might be what determines the true speed and direction of our galaxy. This could mean that our entire motion through the universe is influenced not just by gravity, but by the hidden force of void repulsion. And if that's true, then we might need to rewrite the way we think about cosmic motion entirely. The traditional picture of galaxies moving purely due to gravitational attraction might be only half the story. The other half might involve the unseen influence of vast, empty spaces, voids like the Dipole Repeller, that act as invisible hands shaping the motion of galaxies across the cosmos. So what does all of this mean for the future of astronomy? It means that voids are no longer just empty regions to be ignored. They are active players in the grand structure of the universe. It means that studying voids like the Dipole Repeller could help us answer fundamental questions about dark matter, dark energy, and the fate of the universe itself. As new telescopes and observational techniques come online, we will be able to map these cosmic voids in greater detail than ever before. The Euclid telescope, the Nancy Grace Roman Space Telescope, and future cosmic surveys will give us unprecedented insights into how these voids shape the universe. We may soon discover even more powerful repelling voids, each playing a role in the movement of galaxies on a scale we can barely comprehend. The Dipole Repeller has already changed our understanding of the universe, but it is only the beginning. There is so much more to uncover, and as we continue to explore the hidden forces shaping our cosmic journey, we may find that the greatest mysteries of all lie not in what we can see, but in what we cannot. If voids like the Dipole Repeller are actively shaping the motion of galaxies, then we have to ask, how many of these cosmic repellers are out there? Could our Milky Way be caught in a vast network of invisible forces, each pushing and pulling galaxies in different directions? And if these voids play such a significant role, why did it take us so long to notice them? One reason is that the nature of voids makes them incredibly difficult to study. Unlike galaxy clusters, which shine brightly with billions of stars, voids are, by definition, dark, empty, and nearly invisible. Astronomers have to infer their presence based on the motion of galaxies around them, like trying to detect the presence of wind by watching leaves swirl in the air. For years, astronomers focused almost exclusively on regions of high density, massive galaxy clusters, superclusters, and the gravitational pull of dark matter. But the discovery of the Dipole Repeller has forced scientists to rethink this approach. If underdense regions can have just as much influence as overdense ones, then our entire understanding of cosmic motion might need to be rewritten. This realization has led to a growing interest in studying cosmic voids, not just as passive regions of empty space, but as dynamic structures that shape the entire universe. Some researchers even believe that voids might hold the key to understanding the very fabric of spacetime itself. One of the most intriguing possibilities is that voids could be linked to dark energy, the mysterious force responsible for the accelerating expansion of the universe. Since dark energy appears to be strongest in regions with little to no matter, voids might actually be hotspots for dark energy activity. If this is true, then the Dipole Repeller might be more than just an underdense region. It could be a direct manifestation of dark energy at work. In other words, the very reason the Milky Way is being pushed away might be because we are seeing dark energy exerting its influence in real time. This would have huge implications for our understanding of the cosmos. If voids are amplifying dark energy, then mapping these voids could help us determine how dark energy evolves over time. It could even give us clues about whether dark energy is truly a constant force or if it changes over billions of years. But it gets even stranger. Some theories suggest that cosmic voids might not just be influenced by dark energy, they might be generating it. According to this idea, voids could be regions where exotic physics is taking place, producing dark energy through mechanisms we don't yet understand. This would mean that voids are not just passive gaps in the universe, but engines of cosmic expansion, driving the acceleration of the cosmos itself. If this is true, then the Dipole Repeller could be one of the most important objects in the universe. It might be providing us with direct evidence that dark energy is not just an abstract concept, but a tangible force at work in shaping the motion of galaxies. This could also explain why the Milky Way's motion is so unusual. If the Dipole Repeller is pushing us away, and the Shapley supercluster is pulling us in, then we are essentially caught in a cosmic tug-of-war. But what if there are even more forces at play? Some researchers believe that the motion of our galaxy might be influenced by multiple repellers and attractors at once. Instead of moving in a straight line, the Milky Way might be following a more complex, curving trajectory through space, shaped by the combined effects of multiple voids and clusters. This could mean that our entire understanding of cosmic motion is too simplistic. Instead of thinking of galaxies as being pulled in a single direction, we might need to consider a more dynamic model, one in which galaxies are constantly shifting and changing course due to the influence of multiple competing forces. And if that's the case, then the Dipole Repeller is just one piece of a much larger puzzle. There could be other, even more powerful repelling voids out there, ones that we haven't even discovered yet. In fact, some scientists have speculated that there could be a whole network of voids shaping the structure of the universe. Just as galaxies form along filaments, creating a vast cosmic web, voids might form their own interconnected system, influencing the movement of matter on the largest scales. If this is true, then the universe is not just a collection of galaxies, it's a dynamic system of attractions and repulsions, a vast interplay of forces shaping the cosmic landscape. But this idea raises even deeper questions. If voids are so influential, then why do we see certain large-scale patterns in the universe? For example, why do some regions have an unusually high concentration of galaxies, while others remain almost completely empty? One possibility is that voids are not just pushing galaxies around randomly, but are actually helping to organize the structure of the universe. Some researchers believe that the presence of voids might be responsible for the formation of superclusters, giant structures made up of thousands of galaxies. If this is true, then voids are not just gaps between galaxies, but fundamental components of cosmic evolution. They might be playing an active role in shaping the distribution of matter, determining where galaxies form, and influencing how structures evolve over time. But this idea leads to an even more mind-bending possibility. What if voids are connected to the fundamental nature of spacetime itself? Some physicists have speculated that voids could be regions where spacetime behaves differently than in other parts of the universe. If voids contain little to no matter, then they might also have different properties when it comes to the expansion of space. This could mean that voids are not just empty regions, but places where the very fabric of reality is different. Some theories even suggest that voids might be linked to quantum fluctuations, tiny disturbances in spacetime that could have profound effects on the structure of the universe. If this is true, then studying the dipole repeller might give us insights into the nature of spacetime itself. It could help us understand how the universe expands, how dark energy operates, and even whether new physics is hiding in these vast cosmic voids. The more we study the dipole repeller, the more questions arise. Is it a unique feature of our local universe, or are there many other repelling voids out there? Is it linked to dark energy, or is it an entirely separate phenomenon? Could it help us understand the true nature of dark matter? One thing is certain. This discovery has changed the way we think about cosmic motion. No longer can we assume that galaxies move purely due to gravitational attraction. The presence of a repelling force means that the universe is far more dynamic and complex than we ever imagined. And the implications of this discovery are only just beginning to be explored. As our telescopes become more powerful and our simulations more advanced, we will continue to uncover new insights into the hidden forces shaping the cosmos. The dipole repeller is a reminder that the universe is full of mysteries, some of which challenge our deepest assumptions about how reality works. It is a force we cannot see, yet it influences the very motion of our galaxy. It is a void, yet it has the power to shape the cosmos. And it is just one piece of a much larger, even more mysterious puzzle, one that we are only beginning to understand. If voids like the dipole repeller can exert such a powerful influence on galaxies, then we must reconsider the fundamental forces shaping cosmic evolution. Traditionally, gravity has been seen as the dominant force governing large-scale motion, but what if repulsion plays just as crucial a role? This realization forces us to rethink not only the motion of the Milky Way but the very structure of the universe itself. The standard model of cosmology assumes that the universe is shaped primarily by the gravitational pull of massive objects, such as galaxy clusters and dark matter halos. But the discovery of the dipole repeller suggests that vast underdense regions may be just as important. If voids can push galaxies away with such force, then we may need to develop a more sophisticated model that accounts for both attraction and repulsion on cosmic scales. This raises an interesting question. What exactly is causing this repulsion? Unlike gravitational attraction, which is well understood and follows precise mathematical laws, cosmic repulsion is a much stranger phenomenon. Is it purely a result of the absence of mass, or is there something more at play? One possibility is that repulsion is an emergent property of the way matter and energy are distributed in the universe. When large regions of space become devoid of galaxies, the surrounding matter may respond in a way that generates a kind of negative pressure, pushing away nearby galaxies. If this is the case, then voids may not be passive empty spaces but dynamic regions with properties that influence cosmic expansion. Another possibility is that voids amplify the effects of dark energy. Since dark energy is thought to drive the accelerated expansion of the universe, it stands to reason that regions with little to no matter might be more strongly affected by this mysterious force. If dark energy acts more intensely in voids, then the dipole repeller could be a visible manifestation of this effect, a place where dark energy's influence is more pronounced than in denser regions. This idea aligns with recent observations suggesting that voids expand faster than the surrounding universe. Some studies have found that cosmic voids appear to be stretching at a different rate than galaxy clusters, hinting that the effects of dark energy may not be uniform across the cosmos. If true, this could mean that voids play an even larger role in cosmic acceleration than previously thought. But what if the dipole repeller is not just a natural feature of the universe, but something more exotic? Some theorists have speculated that voids like the dipole repeller might be connected to unknown physical processes that go beyond our current understanding of physics. For instance, could the dipole repeller be evidence of a cosmic-scale quantum effect? In quantum mechanics, empty space is never truly empty. It is filled with fluctuating energy fields and virtual particles that pop in and out of existence. Some researchers have proposed that large cosmic voids might exhibit quantum properties on a grand scale, potentially influencing the motion of galaxies in unexpected ways. Another intriguing possibility is that voids could be linked to the topology of the universe itself. Some models suggest that space-time might have subtle large-scale curvature that creates regions of expansion and contraction. If this is the case, then voids like the dipole repeller could be shaped by deeper geometrical properties of the cosmos, properties that we are only beginning to explore. And then there's the truly mind-bending idea that voids might be remnants of processes from the early universe. Some theories propose that voids could be the leftover scars of cosmic inflation, the rapid expansion that occurred moments after the Big Bang. If voids like the dipole repeller are relics of this ancient event, then studying them could provide clues about the conditions that shaped the universe billions of years ago. But the implications of the dipole repeller don't stop there. If repelling voids are as influential as attracting clusters, then we may need to completely rewrite the way we map the cosmos. Astronomers have traditionally used galaxy clusters as reference points for understanding cosmic structure, but if voids are just as important, then we need to rethink our models of cosmic motion. This could also impact our understanding of the fate of the universe. If voids continue to expand and push galaxies apart, then over billions of years, the universe may become even more fragmented than we thought. Instead of a slow, uniform expansion, we might be witnessing a more complex process in which galaxies are funneled into isolated regions, separated by ever-growing voids. Could this be the beginning of an entirely new phase of cosmic evolution? If voids like the dipole repeller continue to grow, then eventually, galaxy clusters may become even more isolated, drifting apart at an accelerating rate. This could mean that the universe will not only expand but structurally evolve in ways we don't yet fully understand. And if voids are linked to dark energy, then understanding them could be the key to unlocking the biggest mystery of all: what will ultimately happen to the universe? Will dark energy continue to push everything apart until all galaxies disappear beyond the cosmic horizon? Or could voids themselves change over time, shifting the balance between attraction and repulsion in ways we haven't yet predicted? These are the questions that make the dipole repeller such a fascinating and important discovery. It is not just a random empty region, it is a clue to something much deeper, a hidden force shaping the very structure of reality. The more we study it, the more we realize that our assumptions about the universe may have been too simple. The cosmos is not just a collection of galaxies obeying the pull of gravity, it is a vast, dynamic interplay of forces, with invisible structures like the dipole repeller exerting a profound influence on everything we see. And yet, despite all these discoveries, we are only scratching the surface. The more we look into the depths of space, the more we realize how little we truly understand. The dipole repeller is not just a void, it is a challenge to our understanding of physics, a reminder that the universe is still full of surprises waiting to be uncovered. And so, we continue to search, to question, to push the limits of our knowledge. Because every time we think we have the answers, the universe presents us with another mystery, one that forces us to look deeper, to rethink what we know, and to wonder what else might be hiding in the darkness between the stars. If voids like the Dipole Repeller are playing a role in shaping the large-scale motion of galaxies, then the entire cosmic web may be more dynamic than we ever imagined. Rather than a simple interplay of gravitational attraction, we may be dealing with a complex system in which repelling and attracting forces work together in ways we have yet to fully understand. Consider what this means for the broader structure of the universe. We often picture the cosmos as a vast network of galaxies connected by filaments, with clusters forming dense nodes in this web-like arrangement. But what if these structures are not only being pulled together but also pushed apart by unseen forces? If cosmic voids act as repellers, then the universe is not simply growing in size, it is actively evolving in structure, with galaxies being funneled into certain regions while being pushed away from others. This has huge implications for our understanding of cosmic expansion. The Standard Model tells us that the universe is expanding due to dark energy, but the discovery of the Dipole Repeller suggests that expansion may not be uniform. Instead, it could be shaped by the complex interplay of both attraction and repulsion. Could it be that dark energy is not the only force at work? What if the expansion of the universe is being influenced by a yet undiscovered property of cosmic voids? Some researchers have suggested that voids might act as amplifiers of dark energy, intensifying its effects in certain regions. If this is true, then studying voids like the Dipole Repeller could provide crucial insights into the nature of dark energy itself. But here's where things get even stranger. If repelling voids are a real and significant force in the universe, then we have to ask, what happens if they grow stronger over time? If voids continue to expand and push galaxies away, then the large-scale structure of the universe may change in ways we have not yet predicted. One possibility is that over billions of years, galaxies will become more isolated, drifting into separate superclusters with vast empty regions between them. This would mean that the observable universe would become increasingly fragmented, with cosmic voids playing an ever larger role in shaping its evolution. Another possibility is that repelling voids could affect the rate of cosmic expansion in unpredictable ways. If voids exert a kind of pressure on surrounding galaxies, then their influence could either accelerate or decelerate the overall expansion of the universe. This raises the possibility that voids could be a missing piece in our understanding of cosmic acceleration, one that could potentially challenge existing models of dark energy. And then there's the truly mind-bending idea that voids might not be empty at all. What if the Dipole Repeller is not just a void, but a region of space dominated by some unknown form of matter or energy? Some researchers have speculated that cosmic voids could contain exotic forms of dark matter or even remnants of ancient cosmic structures that have yet to be detected. This leads to an even deeper mystery. If voids contain unknown forces, could they be gateways to new physics? Could they be linked to higher dimensions, or even parallel universes? Some speculative theories suggest that large cosmic voids could act as portals to other regions of space-time, with matter and energy flowing between them in ways we do not yet understand. At this point, we have to ask ourselves, are we missing something fundamental about the universe? If repelling voids like the Dipole Repeller are real, then they challenge our basic assumptions about how cosmic structures form and evolve. They suggest that the forces shaping the universe are more complex than we ever imagined, that attraction and repulsion may be two sides of the same cosmic equation. And yet, despite all these questions, we are still only beginning to understand the true nature of the Dipole Repeller. We know that it is influencing the motion of our galaxy, but we do not yet fully understand why. We know that voids may play a crucial role in cosmic expansion, but we do not yet have a complete model to explain their effects. This is what makes the Dipole Repeller such a fascinating mystery. It is not just an empty region of space. It is a key to unlocking some of the deepest secrets of the universe. And so, the search continues. Astronomers are using ever more advanced telescopes and simulations to study the structure of cosmic voids, hoping to unravel the hidden forces at work in the vast emptiness of space. Each new discovery brings us closer to understanding the true nature of the universe, yet with each answer, new questions emerge. What is the ultimate fate of the universe? Will voids like the Dipole Repeller continue to expand, reshaping the cosmic landscape in ways we cannot yet predict? Or is there a deeper force at work, one that we have not yet even begun to comprehend? One thing is certain, the universe is far more complex and mysterious than we ever imagined. And as long as there are questions to be answered, the quest for understanding will continue. The idea that our galaxy is not just falling towards something massive, but also being pushed away by something unseen, forces us to reconsider how we think about gravity and cosmic motion. For a long time, astronomers assumed that large structures in space, such as the Great Attractor, were the primary influence on the movement of galaxies. But now, the Dipole Repeller suggests that voids, which were once thought to be empty and passive, might actually have a much more active role in shaping the universe. The concept of repelling forces on a cosmic scale is still relatively new, and it challenges our traditional understanding of how gravity works. Gravity has always been seen as an attractive force. It pulls things together. But in the case of the Dipole Repeller, we see the opposite effect. If voids can push galaxies away, what does that tell us about the fundamental nature of space itself? One possibility is that the Dipole Repeller isn't just a lack of matter, but rather a region with unusual properties that amplify the effects of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, but its nature remains unknown. Some researchers have suggested that cosmic voids could be amplifying dark energy's effects, creating local variations in expansion that push galaxies in certain directions. If this is true, then voids like the Dipole Repeller may hold the key to understanding why the universe's expansion is speeding up. But there's another layer to this mystery. If voids can influence the motion of galaxies, does that mean they have a form of energy or structure that we haven't yet detected? Some physicists have speculated that voids might not be truly empty, but rather filled with an exotic form of dark matter or even a completely unknown type of energy. If so, this would represent a major shift in our understanding of cosmic physics. And what if this repelling force is not just a passive byproduct of expansion, but an active force in its own right? Could voids be generating a form of pressure that pushes matter away? Some theories suggest that cosmic voids might act like bubbles of negative energy, repelling nearby galaxies and reshaping the large-scale structure of the universe. If this is true, then the Dipole Repeller is not just a curiosity, it is a fundamental piece of the cosmic puzzle. It could explain why galaxies are distributed the way they are, why some regions of the universe are denser than others, and even why the universe is expanding at the rate it is. But here's where things get even stranger. If voids like the Dipole Repeller play an active role in cosmic motion, then they might not be static structures. Instead of being fixed in place, these voids could evolve over time, changing the way they interact with surrounding galaxies. Some simulations suggest that voids can merge and grow, becoming even larger as the universe expands. If this is the case, then the influence of the Dipole Repeller could become even stronger over billions of years, pushing galaxies farther apart and reshaping the cosmic web. This raises a profound question: what happens in the far future if these repelling forces continue to grow? If voids keep expanding and pushing matter away, then the universe may become increasingly fragmented, with galaxies becoming more isolated from each other. This would mean that in the distant future, the observable universe could look very different from what it does today. Instead of a web of interconnected galaxies, we might see isolated pockets of matter, separated by vast, empty voids. Could this be the ultimate fate of the universe? Some cosmologists believe that if dark energy continues to drive expansion, and if voids continue to push matter apart, then galaxies will eventually become so distant from each other that they will no longer be able to see or interact with one another. In this scenario, the universe would become a collection of lonely islands of matter, adrift in an ever-growing cosmic sea of emptiness. But could there be an even deeper mystery lurking within the Dipole Repeller? Some researchers have speculated that voids might be more than just regions of empty space. They might be the remnants of something far older and stranger. Could they be the echoes of ancient cosmic structures that existed in the early universe? Or could they be evidence of processes that took place before the Big Bang? One possibility is that voids like the dipole repeller could be linked to quantum fluctuations in the early universe. If these fluctuations created regions of higher and lower density, then the voids we see today might be the result of those early variations being amplified over billions of years. If this is true, then studying the dipole repeller could give us insights into the conditions that existed just moments after the Big Bang. Another possibility is that voids could be connected to higher dimensional physics. Some theories suggest that our universe may be just one layer of a much larger, multidimensional reality. If this is the case, then voids like the dipole repeller could be regions where the effects of other dimensions leak into our own, creating unusual gravitational effects that push matter away. And then there's the truly mind-bending idea that voids could be linked to parallel universes. Some speculative theories suggest that voids might be areas where our universe interacts with other universes in a vast multiverse. If this is true, then the dipole repeller could be more than just a cosmic void. It could be a boundary between our reality and another, influencing the motion of galaxies in ways we can barely begin to understand. Whatever the answer is, one thing is clear: the dipole repeller is not just an empty patch of space. It is an active force shaping the motion of galaxies, challenging our understanding of gravity, and possibly holding the key to some of the biggest mysteries in cosmology. And yet, despite all our theories, we are still only scratching the surface. The dipole repeller is a reminder that the universe is far more complex and mysterious than we ever imagined. Every new discovery raises more questions, pushing us to keep exploring, to keep searching, and to keep questioning everything we think we know about the cosmos. As technology advances and we build more powerful telescopes and simulations, we may finally uncover the true nature of the dipole repeller. But for now, it remains one of the greatest unsolved mysteries of space, an invisible force, pushing us toward the unknown. The dipole repeller is not just an isolated phenomenon, it is part of a much larger and more intricate cosmic landscape. The universe is structured like a vast web, with filaments of galaxies, clusters, and superclusters forming dense regions of matter. In between these filaments are immense cosmic voids, regions that contain far fewer galaxies than expected. The dipole repeller sits in one of these voids, and its unusual effect on the Milky Way's motion suggests that voids are not just passive gaps in the cosmic web but active players in the large-scale structure of the universe. But how exactly does an empty region exert such a strong influence? If the dipole repeller lacks mass, it shouldn't be able to pull or push galaxies around. And yet, studies show that it does. The explanation lies in the fact that our motion through the universe is dictated by both attraction toward dense regions and repulsion from low-density regions. In the case of the Milky Way, it is being drawn toward the Great Attractor, a dense region of space filled with galaxies and clusters. However, at the same time, it is being pushed away from the dipole repeller, which is an unusually empty void. This leads to a crucial question: why is this void so empty? The most straightforward explanation is that it is simply a region where galaxies never formed due to random density fluctuations in the early universe. In the moments after the Big Bang, tiny variations in density led to some areas accumulating more matter while others remained relatively empty. Over billions of years, these small differences were amplified by gravitational attraction. Denser regions pulled in more matter, while emptier regions lost even more as surrounding galaxies were drawn away. But could there be a more exotic explanation? Some physicists have proposed that voids like the dipole repeller might not be entirely empty, but could contain an unusual form of dark matter that behaves differently from normal matter. Unlike the dark matter that clumps around galaxies, creating the vast structures we see in the universe, this form of dark matter could be more diffuse, filling the void but creating a kind of negative gravitational effect. This brings up another possibility: the influence of dark energy. Dark energy is the mysterious force that causes the universe to expand at an accelerating rate. While its effects are usually discussed on a cosmic scale, some researchers have speculated that local variations in dark energy density could create pockets where its effects are stronger. If the dipole repeller sits in a region of space with a higher concentration of dark energy, this could create an outward pressure that repels galaxies, explaining why the Milky Way is being pushed away. If this is true, then the dipole repeller could be a window into the nature of dark energy itself. Right now, dark energy is one of the biggest mysteries in physics. We know it exists because we can see its effects on the expansion of the universe, but we don't know what it is. If voids like the dipole repeller are influenced by dark energy, then studying them could help us understand what dark energy is made of, how it interacts with normal matter, and whether it changes over time. Another fascinating possibility is that the dipole repeller is not just a void, but the remnant of an ancient cosmic event, something that happened billions of years ago that left behind a region of low density. Some cosmologists have suggested that voids like this could be the result of massive quantum fluctuations in the early universe. These fluctuations, which happened in the first fractions of a second after the Big Bang, could have created regions of space where matter was effectively pushed out, leaving behind a long-lasting void. But there's an even more mind-bending idea. What if the dipole repeller is not just a void, but an actual tear in the fabric of space-time? Some speculative theories suggest that voids might be connected to higher-dimensional physics, regions where the effects of another dimension influence our own. If this were the case, then the dipole repeller could be more than just an empty region. It could be a boundary between our universe and something else. This idea ties into some of the more extreme theories in modern physics, such as the possibility that our universe is just one of many in a vast multiverse. If parallel universes exist, then voids like the dipole repeller could be places where the influence of another universe leaks into our own. This could explain why it has such an unusual effect on galactic motion. Perhaps it is not just a void, but a gravitational imprint left by something beyond our universe. Of course, these ideas remain speculative, but the very existence of the dipole repeller challenges our understanding of how the universe works. Traditionally, astronomers have focused on areas of high density, galaxy clusters, superclusters, and massive gravitational wells. But the dipole repeller suggests that empty regions are just as important. If voids can shape the motion of galaxies, then they might play a much bigger role in cosmic evolution than we ever realized. The next step in understanding the dipole repeller will come from more detailed observations of cosmic voids. Astronomers are already mapping the large-scale structure of the universe with greater precision than ever before. Future telescopes, such as the Vera C. Rubin Observatory and the Euclid Space Telescope, will provide even more data on the distribution of matter and dark energy. If we can map the properties of the dipole repeller in greater detail, we may finally unlock the secrets of why it exists and how it influences the universe. But even if we solve the mystery of the dipole repeller, it will likely raise even more questions. Does every galaxy experience a similar repelling force from a void? Are there other voids with even stronger effects? And if so, could they explain some of the unexplained motions of galaxies across the cosmos? For now, the dipole repeller remains one of the most intriguing mysteries in cosmology, a vast, unseen force shaping the motion of our galaxy and challenging our understanding of space itself. Whether it is a simple void, a hidden reservoir of dark energy, or something even stranger, one thing is certain: the universe still holds many secrets, and the more we learn, the more mysterious it becomes. The dipole repeller is a stark reminder that cosmic voids are not mere empty spaces. They actively shape the universe. Traditionally, astronomers focused on regions of high density, galaxy clusters, superclusters, and massive gravitational wells, because those are where the most visible action takes place. But the discovery of the dipole repeller suggests that the so-called empty regions of the universe are just as significant in determining the motion of galaxies. This revelation forces us to rethink our entire understanding of large-scale cosmic dynamics. One of the biggest questions surrounding the dipole repeller is whether it is a unique phenomenon, or if similar voids exist throughout the universe, exerting comparable forces. Given that the Milky Way is being pushed away from the dipole repeller while being pulled toward the Shapley supercluster, it suggests that this push-pull interaction could be common across the cosmos. If so, it would mean that every galaxy is experiencing a complex dance between attraction and repulsion, shaped by both massive clusters and immense voids. This brings up an even deeper question. If voids play such a crucial role in shaping the motion of galaxies, could they also influence the overall structure of the universe itself? When we look at large-scale cosmic maps, we see the universe arranged in a vast web-like structure, with filaments of galaxies connecting dense regions while voids act as gaps in between. But what if these voids are actively expanding due to some unknown force? If cosmic voids grow larger over time while galaxy clusters become denser, it could mean that voids play a role in cosmic evolution far greater than previously imagined. There are a few possible explanations for why the dipole repeller, and voids in general, could be expanding. One possibility is that the same mysterious force that causes the expansion of the universe, known as dark energy, is particularly concentrated in these voids. Dark energy is still one of the biggest unknowns in physics, but it is responsible for the accelerated expansion of the cosmos. If voids like the dipole repeller contain a higher concentration of dark energy, they might exert an even stronger repelling force than expected, pushing galaxies away at an accelerated rate. Another possibility is that voids are not just empty spaces but regions where matter behaves differently. Some theories propose that voids might be filled with an exotic form of dark matter that doesn't clump together like ordinary dark matter but instead creates a kind of repelling force. If such a form of dark matter exists, it could explain why the dipole repeller has such a strong influence on galactic motion. But there is an even more intriguing and speculative possibility. What if the dipole repeller is evidence of an interaction between our universe and another universe? Some theories in modern physics suggest that our universe could be part of a vast multiverse, where multiple universes coexist but rarely interact. If voids like the dipole repeller are regions where the gravitational influence of another universe is seeping into our own, it could explain why we see such an unusual repelling force. This idea is not as far-fetched as it might seem. Some variations of string theory propose that our universe is just one of many three-dimensional membranes, or branes, floating in a higher dimensional space. If another universe is nearby in this higher dimensional space, its gravitational influence might be affecting our own. This could manifest as unexplained forces in certain regions of the cosmos, such as the dipole repeller. If true, this would be one of the most groundbreaking discoveries in physics, as it would provide evidence that our universe is not alone. It would also open up entirely new questions. Could information or even matter cross between universes? Could voids like the dipole repeller be portals to other realities? These are questions that, for now, remain in the realm of speculation, but the fact that we are even considering them shows just how much the dipole repeller challenges our understanding of the universe. More immediate research, however, focuses on mapping the full extent of the dipole repeller and studying how other cosmic voids behave. If we find more voids exerting similar forces, it would suggest that this is a universal phenomenon rather than an isolated case. Some of the most advanced telescopes and space missions, including the Vera C. Rubin Observatory and the Euclid Space Telescope, are designed to help us map these vast structures with unprecedented precision. One of the key goals of these missions is to create a detailed three-dimensional map of the universe that includes not just galaxies and clusters, but also the invisible influence of voids. If we can track the motion of thousands of galaxies and identify similar repelling forces elsewhere, it would help confirm whether the dipole repeller is part of a larger pattern. For now, though, the dipole repeller remains one of the most intriguing cosmic mysteries. It is an unseen force that is actively shaping the motion of our galaxy, and possibly many others. Whether it is simply a natural void, a manifestation of exotic dark energy, or something even more profound, it forces us to confront the possibility that the universe is far more complex than we ever imagined. The implications of the dipole repeller go beyond just the motion of the Milky Way. It raises profound questions about the very structure of the universe and how galaxies are distributed across cosmic time. Traditionally, astronomers have viewed the cosmos as a vast web of interconnected filaments, where galaxies cluster together due to gravitational attraction. However, the presence of repelling forces suggests that the large-scale structure of the universe is not just shaped by what pulls matter together, but also by what pushes it apart. One of the most fascinating aspects of this discovery is how it changes our perception of cosmic balance. For centuries, astronomers have focused on gravity as the primary force governing the movement of celestial bodies. Everything from the orbits of planets to the clustering of galaxies was thought to be dictated by gravitational attraction. But the dipole repeller challenges this view, suggesting that gravity alone is not enough to explain the motion of galaxies on the largest scales. This revelation raises new questions about the fundamental forces of the universe. Could there be a yet undiscovered force that counteracts gravity on cosmic scales? While dark energy is one possibility, some physicists speculate that our understanding of gravity itself might need revision. Alternative theories of gravity, such as modified Newtonian dynamics, MOND, and tensor vector scalar gravity, TeVS, propose that gravity behaves differently in regions of low density. If these theories are correct, voids like the dipole repeller could provide the missing link in understanding how gravity operates across different environments. Another key aspect of the dipole repeller mystery is the question of its origins. How did such a massive void come to exist in the first place? The standard model of cosmology suggests that the universe began as a nearly uniform field of matter and energy. Over time, small fluctuations in density grew due to gravitational attraction, forming the galaxies, clusters, and superclusters we see today. But if voids like the dipole repeller are pushing galaxies away, it suggests that these regions may have evolved differently from the rest of the universe. One possible explanation is that voids are the result of cosmic inflation, the rapid expansion of the universe in the first fractions of a second after the Big Bang. If certain regions of the early universe expanded faster than others, they may have developed into large-scale voids. Another possibility is that interactions between dark matter and dark energy played a role in sculpting these vast empty spaces, creating repelling forces that persist to this day. The study of cosmic voids is still in its early stages, but astronomers are now beginning to recognize their importance. While galaxies and clusters may be the most visible structures in the universe, voids could hold the key to understanding some of the deepest mysteries in cosmology. If the dipole repeller and similar voids are actively shaping the motion of galaxies, it suggests that the empty regions of the universe are far from passive. They are dynamic, evolving structures that influence the fate of cosmic matter. As scientists continue to map the universe in greater detail, they hope to uncover more about the role of voids in cosmic evolution. Future telescopes and surveys will provide high-resolution 3D maps of the universe, allowing astronomers to track the movement of galaxies with unprecedented precision. If we can identify more repelling forces like the dipole repeller, it will help confirm whether this phenomenon is a rare anomaly or a fundamental aspect of cosmic structure. For now, the dipole repeller remains an open question, one of the most intriguing puzzles in modern astrophysics. It challenges our assumptions about how the universe works, forcing us to consider new possibilities about gravity, dark energy, and the large-scale architecture of the cosmos. Whether it is simply a void, a remnant of cosmic inflation, or something even stranger, one thing is certain: the universe is still full of surprises. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.